So we had some food for thought in this video. A very warm welcome to all of you to the Royal Swedish Academy of Engineering Sciences, IVA. Both you who are here today at the Wallenberg Hall in Stockholm, and also those of you who are following us online. My name is Tuula Teeri, and I'm the president of IVA, and a very happy one today because I can actually see people in front of me. So the restrictions are finally starting to be lifted, and in the future I'm sure that we will see more and more events where we fill the whole Wallenberg Hall here in Stockholm. The music video that you just saw is a jazz tune which was rearranged, as you saw, using only items of plastic, and it was made for the occasion of the 100th anniversary of IVA 2019. I think it also illustrates quite well, how these difficult issues in society need collaboration, of course, between academia and industry and politicians, but also science and art. So the plastic, of course, as you know, is the theme for our seminar also today. And like it was useful material for the music, it is useful material still in many aspects of our lives in modern societies. But as we know, it's also linked to issues which are concerning both the energy and the environment, which we also saw in the artistic presentation. So IVA is an academy. We have a mission to advance technology and economics, but also to promote the development of industry and business in Sweden. And to do so, we like to call ourselves as a bridge builder between research, business, and policymakers. We have had our own projects on the issues around plastic, and we have also been participating in providing science-based advice to the European Commission regarding plastics. So some of our fellows have been contributing to the work that has been collecting the fact base for the science advisors of the European Commission so that they can then advise the Commission. And it's of course important, this kind of task. It's not always very easy, as I'm sure many of you have also experienced, to have these bridges. But it is important so that we can come up with a holistic approach for plastic sustainability. So research and business and policy must move in the same direction if we are going to solve this and many other of our problems. So we will today focus on research and the kind of research that is demonstrating of both international and interdisciplinary collaborations. I was listening to a forum discussion which was streamed from Kyoto just this morning. And when you listen to the experts, the best experts worldwide, you know, there are a few things that they always lift. And one of the things is that it has become the kind of standard theme in these kind of discussions today, and it is that our problems are global, and therefore they cannot be solved within any country alone. And it's also that they are so complex that you cannot solve them only with one discipline, but you do have to actually learn from each other, both from countries and also for different science base. So I'm really looking forward to this discussion today, and I hope that you will have a really good time engaging in this discussion. But before we start, let me first give the floor to our co-organizers. I'd like to welcome to the scene first the French ambassador to Sweden, Etienne de Gonneville. And then after that, the co-organizer, the CEO of the Swedish Foundation for Strategic Environmental Research, Mistra, Anna Jöborn. And please come and give your introductions. Thank you.
Thank you, Tula. Thank you for organizing this conference today. Dear friends, chers amis, chers Avenner, just a few words on behalf of the French Embassy and the French Institute in Sweden to welcome you all to this conference on plastic recyclability and the circular economy, which we have at last been able to organize. I'd like to thank our partners today, the Royal Swedish Academy of Engineering Sciences, the Swedish Foundation for the Strategic Environment Research, through the program STEPS, and the Royal Institute of Technology. We've had this project for this conference for a long time within the framework of the French-Swedish Strategic Partnership for Innovation and Green Solution, and within also the framework of the implementation of the European Plastic Pact. Today, the fact that, again, at least we are able to organize it with such a big participation in person, but also virtually, is going to materialize at the level of research the reality of our partnership between France and Sweden, the reality also of the European Green Deal, and our seriousness in implementing the UN Sustainable Development Goals, in particular the goal number 12, ensure sustainable consumption and production patterns. So it's really, as Tula described, a worldwide endeavor. But today it is also about plastic and about Europe and the way we as Europeans can take this matter in our own hands. Seen from the French Embassy and the French Institute, we have 4 ambitions for the conference today. First of all, allow researchers in the same field to get information on European frameworks and the way they are being implemented in each of our countries, especially under the Plastic Pact. Second, allow researchers to get to know each other better, establish new networks, and identify potential partners to build research projects. And not only, as Tula described, in the field of research, but across different domains that are working on plastics under an approach which is the approach of the Plastic Pact, actually, which is a very multi-actor way of tackling current challenges. The third horizon, the third ambition for us, is to have more French, Swedish, and French Nordic teams submitting projects under the Horizon Europe program, and to take advantage of the budgets that have been set aside under the program. Fourth and last one is to strengthen European research and European excellence in an area that is essential for the future of the world economy. A few days ago, I visited the old town of Stockholm, Gamla stan, and I learned during that visit that for centuries, the people of Stockholm or the old city, which is built on a rock, had the habit of just pushing the waste into the lake Mälaren. For centuries they did that, and of course they could not drink the water of the lake anymore. They had to rely on a few wells in Gamla stan and on large quantities of beer as well. Stockholm has, since that time, found a better solution for its waste management. But in a way, just pushing the waste is what the whole world is doing today with plastics. And this is why your conference today is so important. I wish you an excellent conference, excellent opportunities to build new contacts and to develop new projects together. Thank you very much.
Thank you for inviting me. And I actually, thanks to the French, we also drink wine nowadays, not only beer in Stockholm. Yes, ladies and gentlemen, ambassador, and in real life persons and Zoom friends. My name is Anna Jöborn. I'm the CEO of Mistra, and it's a great honor to meet here today. And Eva is an excellent place to meet because you are this bridge maker between science, policy, and industry. And also I like the idea of French-Nordic collaboration, and I think it could be very useful in the future in sustainable development of new plastic materials, for example. So collaboration between our countries has a long history. And I think international collaboration and exchange of ideas are key to success in science. I represent Mistra, a foundation funding strategic environmental research. We have done it since 1994. We have invested 5 billion Swedish crowns in strategic environmental research with the aim to fund excellent research that also aims to provide solutions to environmental problems and great challenges that we face in our society today. We finance a wide range of research, including programs on sustainable management of natural resources, transition to low-carbon society, mobility in urban areas, and all sorts of different topics. We promote mission-oriented research, and we make long investments. 8 to 10 years is a normal time period for a Mistra program. And we encourage transdisciplinary research and also systemic and complex-oriented research that target this kind of complex issues. One great area of great importance is finding new, more resource and energy-efficient production processes and developing new materials. And I think plastics is one of these really great inventions. It's very useful material, and we'd like to use it in the future as well, but in a very more careful way. And we need to take care of how we handle it, and we like to support science that also supports a society which is making more circular decisions concerning plastics. So we're proud that the scientists and other key stakeholders, I've met a few from the industry and also policymakers here today, that we work in close collaboration and develop these environmentally friendly, innovative materials and also ways to recycle and reuse these materials in society. We have researchers representing STEPS, Sustainable Plastics and Transition Pathways. We also have resource-efficient and effective solutions. You're going to give presentations during these 2 days. And I'm really looking forward to learn more about the science that you perform. And I also like to encourage collaboration. And I know there is collaboration between the scientists in the programs. And I also think there is a lot of possibilities and ideas that could be brought forward during these seminars. And I think the plastic strategy, the European plastic strategy, and the global ambition to tackle the problems with plastics is a great opportunity for the researchers to make real difference. Not only in Sweden and in Europe, but globally. Thank you so much, and I'm looking forward to listen to your presentations.
Hi, good afternoon, everybody who's present here and also those who are online. You can't imagine how good it feels that we have finally arrived to this day. It seems we have been planning this conference for a long time, at least 1.5 years. And as we all know, that COVID pandemic took over our lives for quite some time, so we had to postpone this conference, and so finally we found this date, and also September. It is Sweden is open, and also some of the neighboring countries have also opened their economy. My name is Rajni Hattie-Kaul. I'm professor in biotechnology at Lund University and also program director for STEPS, that is a research program funded by Mistra. And I would like to take this opportunity to thank Eva, Mistra, as well as the French Institute and Embassy for co-organizing, for helping in co-organizing this conference. So this afternoon, it's a long afternoon. We have about 13 talks, and I'm very grateful that we have been able to attract a lot of good speakers and relevant speakers, both from the funding agencies, policies, and also researchers. So the idea behind this conference, as you already heard, was to bring together French and Nordic researchers. And we have people not only from France and Sweden, but also from other Nordic countries, Denmark, as well as Finland, and tomorrow you will see somebody from Norway as well. Since we are short of time, so I thought what I will do today, I'll be one of the moderators, and together with Professor Ulrika Edlund, will be moderating the sessions today. So I take this opportunity to present our first speaker, that is Osa Steinmark. I don't think anybody would be surprised to have Osa here. She is very well known in Sweden, at least, and she's a materials flow expert and working at Swedish EPA today, and before that she was working at IVL, that is the Swedish Environmental Research Institute. And this is the lady who was responsible for the Swedish plastic strategy, if I may call it. Det går om vi vill. At least the Swedish people must have seen that. So she knows everything of what has happened and what is going to happen. So I leave the word to you, Osa, and thanks for joining us.
Thank you so much for those kind words. I will speak today about the National Plastic Coordination, about our roadmap to sustainable plastic use in Sweden, but I will also give you a brief overview of the European Plastics Pact that was mentioned by the French ambassador here. So I still think it's possible to have a sustainable use of plastic if we really want to, and if we are willing to do the work. And I do think that you are all aware of the problems that we have with plastics. There are also, of course, very many benefits, and I know that I'm speaking to plastic people here, so I know that you are aware of the benefits, but this is what we're trying to tackling. And we did a scenario study at the Swedish EPA last summer, where we tried to our consultants try to describe different scenarios on how we could reach a sustainable plastic use. And as you see, there are 6 different strategies that they came up with. So either we could go for smarter use, which is of course that we use plastic in a smarter way and trying to decrease it also a little bit. We could go for substitution, so changing towards other materials or changing plastic towards plastics. Mechanical recycling, bio-based materials, bio-based plastics and CCU. Chemical recycling, and one scenario where they also suggested that we could stay with the fossil raw material, but if we then want to be carbon neutral, we would need CCS. And I think we thought in the beginning when we did this project that, okay, but we can maybe end up with one scenario, and then we as policymakers, that would be great, right? Because then we would know what to do and how we could try to steer this, what kind of policy instruments that were needed. But that was not really the case. So instead we ended up with the knowledge that, okay, there are so many things that we need to do. Like also Tula said in the beginning, we need to act within all these different areas. As you can see, it's very clear that none of them can solve the problem on their own, so to speak. So we need to work with all of these different areas. And what's also clear is that there are actually huge changes that we need to make. So changing recycling from today's roughly 10% to reaching these 30% of that staple in the middle would mean that we have to go from the 10% that we have today to maybe over 50% of plastic in general. And as I know that you work with plastic, I also know that you know that that's not so easily done. So huge changes and changes within all these areas. And as was also mentioned in the beginning, few things that can be made only by us in Sweden. So we need to also act on a global scale here. Okay, so that was a lot of problems. It's like kind of, wow, how can we solve this? The Swedish government thought that a good idea was to give the EPA the assignment to start up the National Plastic Coordination, which I'm responsible for at the Swedish EPA. And we are the task that we have is to generate knowledge, to collect knowledge, and to spread that to different actors that are in need of the knowledge. So the whole idea is that by getting more knowledge and by transfer it from the person that has it to the person that might need it, by doing that we could sort of change the way that we are working with plastics. And then, as you see on the last point here, we should also create collaboration between these different actors, because none of these changes would be necessary or possible if we don't start to collaborate more. And the National Plastic Coordination should be a driving force in this. So that's kind of new for an authority to be also a driving force, but that's our mission. We should try to unite all these actors. We're working with all actors in the society except for households. And then, of course, we need to have a holistic perspective. It's very easy to end up saying that plastic is bad or plastic is good, but you know that the truth is somewhere in between. So we always need to keep that holistic perspective in mind. And to try to describe where we are going, what a sustainable plastic use is, we at the Swedish EPA created a roadmap. So a roadmap for sustainable plastic use, which was also asked for by all kinds of different stakeholders when we sort of did this investigation, setting up the national coordination and ask for other actors' needs. And the roadmap is supposed to give you common goals on what sustainable plastic use could be. It's supposed to create a uniting understanding of what this change, or what change that is needed, the transformation that we need, and also a common picture of necessary actions. We don't go as far, however, as pointing at different actors saying that you have to do this and you have to do that. That's not in our mandate to do that. But we are trying to encourage for these kinds of action and encourage for the change. And this is how we describe sustainable plastic use. So plastic use in the right applications, in the resource-efficient, climate-effective, non-toxic and circular flows with a minimum of leakage. And you see that so many buzzwords jammed into that sentence. But all of them are important in this matter. And we work with all these 4 different effect areas, as we call them. So if you remember the scenarios and the different change areas for change that they had to come up with, we transformed them into these 4 effect areas. So it's raw material and production with a minimal environmental impact. It's resource efficient use or resource smart use. It's reduced plastic leakage in nature, and then of course significantly increased high quality material recycling. And I don't have time today to go through the roadmap in detail, but very briefly, yes, this is for the resource-efficient use, because that's also linking a lot to the European Plastics Pact. We have described these shifts that we need to go from the yellow staple to the green staple. And of course, in terms of smarter use, it means that we have to be more circular. So circular economy, people would definitely recognize this for all kinds of materials, not only plastic. So I'd like to stress that as well. And in the roadmap, we also have different development areas where we think that development needs to happen. And we do describe different actions and different actions that different actors could take in order to sort of contribute to these development areas. So that was the roadmap, very briefly. And one other thing that the Swedish government thought was a good idea was to join the European Plastics Pact. So what is the European Plastics Pact? Maybe I've heard about Plastics Pacts. It's generated by Ellen Carter Foundation. So there are many national plastics pacts as well, all over the world, not only in EU member states. So why come up with a European Plastics Pact? This is the same picture about problems, but on an EU scale, basically. But the idea of creating a European Plastics Pact is that we do have different situations in different countries that can be dealt with country-wise, but as Tula so nicely stressed in the beginning, this is a global problem, and at least we should act at an EU level. So the whole idea of the pact is to speed up the transformation that could happen on an EU level. And there are 4 target areas set, and it's all going to be done, hopefully, by 2025. And you can see that there are targets around recyclability and reusability, so 100% recyclable and reusable packaging and single-use items is the targeted products here. Then maybe the most controversial goal of the 4, to use 20% less virgin plastics with a 10% absolute reduction. So this is an absolute reduction target, which is maybe seen as controversial by few. And then, of course, increase the recycling rate by 25%. If we are to recycle more, of course, we do need to get the material into the recycling processes. And then use the recycled plastic 30% increase, or at least in 30% in new products. So in order to reach all these goals, if you sign up for the pact, there are, I forgot to say, there are about 179 signatories today, both member states, but also private businesses, but also public organizations. And they have all signed up to contribute to these targets and measuring them on their own businesses, so to speak. And then the idea is that that will contribute to the whole plastic pact. There are working groups assigned to each of these targets, and there is a roadmap. I just put the link there because I don't have time to go through it all. But it's a good roadmap pointing out the activities that now are being carried out. And this is a catastrophic PowerPoint picture in terms that you don't see it at all. But anyway, in the roadmap, you have all these different kinds of activities, more to show that there's lots of things going on. Please look it up in the roadmap instead of trying to read on these slides. The pact is open for anyone to join, so please join. Email RAP, who is hosting the secretariat. and contribute to these targets and to the work done on EU level. So that was all that I was going to say. To finalizing slide with the details of the European Plastics Pact, but also my own contact details in case you need to ask me anything. Thank you.
Tack, Osa. It's really an impressive package of work that you have on your plate right now.
Yeah.
Yes.
Yeah.
So just a question. So this is the European Plastics Pact. So what are the forms of collaboration within the nations, within the Union, to sort of streamline activities so that you don't invent 22 different pound systems around Europe?
that would be something. But no, the member states that are involved in the pact, I think it's around 15 today. We are having a special member state group where we do these kinds of discussions and try to align ourselves, but also try to inspire one another. So, for example, the deposit system, we have a good one in Sweden. They don't in other countries, which is so they're really looking with interest at our deposit system.
So that's part of the legislation, actually. The all countries should have this refund deposit system within a few
within
years,
the
right?
single-use directive that's recommended. It's not legally binding, but it's recommended in order to reach the recycling targets that are set. Yeah.
So you have many different goals here. If you may pick, which one do you think will be the most easiest one to meet, at least approach?
I think
within the time frame that we have.
I think the easiest one is the 30% recycling in products. Looking at you plastic people sitting here, because that's already happening in many products. And I know that there are problems with the food contact materials. Problems. It's not legal, but
yes,
and so on and so forth. But that I think is the easiest one. I think the reduction is the hardest because that would mean that we have to change the way that we look at many different things. So reduction in general is the toughest thing.
Yeah, because that hurts, right? You have to change your lifestyle, and
we think it hurts, but I'm not sure it will hurt so much. But we think it hurts, so that makes it harder.
It does, but that alludes to another thing that I want to talk to you about, because what the past 1.5 years showed us is that when the pandemic hits, your health gets more important than anything else, and people that were so let's do plastic reduction or even plastic elimination turned from one day to another, they're using tens of face masks and shields and whatever. And there are PMMA frames in every store. I mean, we went ballistic on plastics all of a sudden, caring not at all about them being non-recyclable or where they were from renewable resources or not. So that shows us a little bit of dependence on plastics.
Yeah.
So what's your take on that? How long will it take to come back to a more reasonable consumption level? Because now it's crazy, actually, the amount of disposables that we are using in the medical context.
Yeah, I totally agree on that. And already in the investigation that we made in 2018, we actually pointed out that this is not only a resource problem, but also a security problem. We are so depending on all these kinds of single-use items at hospitals, for example. And we all saw what happened when the what do you call this in English? The face things, you know. Supplies didn't work and so on. But to answer your question, I do hope that we will shift back soon. Yes, very soon, because we cannot take too much of this single use. But and to be pessimistic, which I don't really like to be, but you really saw what kind of strange behavior that could be created by a fear of something. And being a bit Greta Thunberg, maybe that's how fearful we should be of the climate change or the resource scarcity that we might end up with and things like that. So maybe we should act a little bit more like that when it comes to changing behaviors.
Yeah, definitely. Yeah, because you also could see a change in people's behavior when it came to, I mean, you were so particular about putting maybe your plastic trash in a recycling bin, but people throw face masks all over, and you see them hanging from trees and in the ocean and everywhere. So it's a change of behavior also that is sort of a hurdle for us. Thank you so much. These are not easy questions to tackle or answer, so sorry for bugging you about it. But it's super nice to hear it from a Swedish perspective. And we were looking forward today to also get the French perspective on the European Plastics Acts, because a lot of things are, of course, going on in France as well. So we were looking forward to welcome Dr. Alexander Levernoy here as the coordinator for the National Plastic Pact in France. But as I understand, we're not able to reach him. Still no contact. So I'm sorry then to say that I will not be able to introduce the next speaker if he's not available. So then, instead from going to the French perspective, maybe we can talk a little bit about how we then collaborate, because there are so many challenges, as Osa points out, and there's also much competence in-house, in Europe, and maybe if we collaborate, we already pointed that out, we can reach much further if we do it together. So there are, of course, opportunities to do so, not in the least the new call for research products that come out now. So the Horizon Europe calls for research projects. And I would like to welcome now Dr. Louise Staffas. You can tell us more about this Horizon Europe package of calls and how it can relate to collaboration within Europe and particularly Sweden and France. Welcome.
Thank you. Bonjour à tous. 6 juin sur distance. Hej alla. Det är roligt att få prata här. So I was invited to talk a little bit about plastic research within the Horizon Europe. And I represent Formas, one of the governmental funding organizations or funding agencies. And it's hard not to talk anything about us first, so that you know the context in which I will speak. So we are a research funding agency, and we contribute to the sustainable development by funding best research. We fund cutting-edge innovation as well. And we synthesize research reviews and within our areas of responsibility, the environmental field. We are actively taking part in dialogues and collaborations on a national as well as international level. And we are also actively working with research communication, because it's only when the research results come out outside the academic corridors that they will actually contribute to a change. Our areas of responsibility are environment, agricultural sciences, and spatial planning. And within these areas, we have national, both open and targeted calls. We have, since a few years back, together with other funding agencies, we have a few national programs that address the societal challenges. And you're welcome to look at our website for more information about those. We also participate in this innovation program called Strategic Innovation Programs, and we actively coordinate one of the programs and also fund 7 of them in totals. We have recently started with innovation calls, besides or in addition to the SIPs. And we are also very active, actually, especially for relative to our size, in international collaborations and on both European and international or global levels. As you can see here, we have several Nordic collaborations. We are very active in EU during the Horizon 2020, as well as now the newly started Horizon Europe. We are a member of the Belmont Forum, which is a global researchers or research collaboration. Multinational calls mostly, but we also have a few bilateral collaborations. So we fund, our budget is around 2 billion Swedish crowns, that is 2 million euros. And with that, we have quite, most of it goes to the national calls, but with that budget, we are still quite a significant player on the international market. So, with that said, that is sort of to say why we can speak a little bit about the Horizon Europe calls. As you probably know, it's the next research frame program after Horizon 2020. It's, I think, the biggest research program ever, with almost 100 billion euros over 7 years. It is addressed, or it addresses the climate change. So it works. It's funded on the UN Sustainable Development Goals, and it also aims, of course, to boost the European competitiveness and growth. And this is just taken from the websites. And what it wants is to, as Ulrika said, to stimulate collaborations over several nations within the European Union, of course. And it also involves very often non-academic partners, like the Horizon 2020 did. So I think you're very familiar with the different pillars of the Horizon Europe. And what I will focus on today, where you can find the plastic research, is in the pillar 2, that addresses the global challenges. And especially in cluster 4 and 6, that's where you find the plastic-related calls mainly. And if you are interested, you can, of course, search for the word plastic, but since it's an important material field, material flow, but it also sorry, I will come back to that later. The plastics in EU, well, the calls and actions within the Horizon Europe, of course, relates to the strategies, various strategies that EU has on plastics, on circular economy, on chemicals, on the Green Deal, etc. So everything is sort of related. There are also a number of partnerships forming that have a strong emphasis on various types of plastic, in particular, but material flows. I will come back to the partnerships and formats a little bit later. And then, as I said, research calls within the clusters, mainly cluster 4 and cluster 6. So this is sort of also from the EU website about cluster 6, that because I will not focus very much on cluster 4 because Formas is not very active there, and in addition there's much more on plastics to be found in the cluster 6. So it aims at reducing the environmental degradation and tackles climate change. And there are several areas of intervention. I will not go through them here and now because this is really just cut and copied from the website. But as you see, there are many practical challenges that are addressed within the cluster 6. And that's, of course, where also the plastic comes in. An overview, sort of what aspects of plastic does cluster 6 address? And it's, of course, microplastics, wherever they are, in air, in soil, in water. It's the single-use plastic and the packaging, of course. A general question of material flow and value chains. And, of course, plastic pollution in general. So those are, but there are a number of calls already addressing the plastics, but this is sort of the essential and an overview. And I think that for details, it's easy to go to the different separate work plans. And then we have the partnerships. And what's the purpose of them? I think you are familiar with those as well. It is a way to enable partners that unite in a more specific question or area of research, and member states to go together and create more dedicated collaborations and more dedicated research calls. And then the researchers, of course, need to contact the agency responsible and active for that particular partnership where an interesting topic for them is. So for us, we are, although we are small, we have engaged in 4 of the new sort of upcoming partnerships: Biodiversa, Driving Urban Transitions, Water for All, and Sustainable Blue Economy. And I dare to say that plastic come in all 4 of these. And we've been involved in the formation of these partnerships from quite the beginning, actually. So we have staff at Formas that can help you and guide you more into detail into those programs. And then we also engage in these 3 so-called co-funded partnerships that are about to start in 2023, where plastic also comes in, although it's not really, they are not formed yet, so we don't know the details about these partnerships. And if you want to find out more, there are of course the Horizon Europe websites, but for the Swedish researchers, you're very welcome to contact us. I guess you will mail out the slides, but you can also go through our websites, of course. At us, it's Karin Perhans, who's main responsible for Cluster 6. We have all the partnerships and various collaboration. It's my colleague Britta Fengström. And then also our sister agency Vinnova, they have national contact points for Horizon Europe in general, for Cluster 4. And for, if you want to address them, I suggest that you go to Johan Lindberg at Vinnova. And we hope that Horizon Europe will be as important research program as the Horizon Europe has been. And of course, the different calls have different conditions regarding balance between research and actors outside the academia. So you need to go and look at the details for each and every specific call. Thank you very much.
Tack, Louise. So many opportunities.
Yes.
So what is the time frame of this Horizon Europe framework?
It is until 2027. Quite classical for the big research programs that were formerly the research frame programs.
Then we have some time ahead to plan and execute research together.
Yes, but time flies. And with the plans of the Plastic Pact, we need to act. Yes.
Yeah, good point. Yes. So, of course, it's always open for questions. And I should say to all of those who are watching online that it's also possible to ask questions. There's a chat window, right? And Elin here will moderate, and if any questions pops up, then we can direct it directly to the speaker. Thank you so much, Louise. So we have many opportunities, but you point out something really important, Louise, and that is that it's not only academic partners that are driving research. It's a collaboration, it's a partnership, and it involves academia, institutes, NGOs, companies. So we also need the perspective from industries, Sweden and in a European context. And someone who can really tell us more about that would be ICAM, Innovation in Chemical Industries in Sweden. Their organization are representing all those industries, and they have the network and they know exactly the drivers, the needs, and the modes of collaboration. So our next speaker can maybe tell us more about this. Henrik Oxfall from ICAM. Can you hear us?
Yes, I can hear you. Thank you very much for letting me participate and give a short talk here today.
We're happy to have you. Please.
Yes, and now I hope you can see my screen as well.
Not yet, but I think someone can arrange it.
I should be sharing my screen.
Yes, just a second. We need to switch screens here. Here we go, please.
There you go. Thank you. Perfect. So, thank you for the introduction. My name is Henrik Oxfall, and I'm coming from ECHEM, Innovation and Chemical Industries in Sweden. We are a trade and employee organization representing plastic and chemical industry in Sweden. Today, I will try to give you a short overview what the plastic industry is focusing on today when it comes to circular and bio-based economy. It's very hard to kind of give the full picture of the full industry, so you should consider this more as my general reflection based on my experience, rather than the complete picture from the overall industry. But first of all, I would just like to take a quick look at the plastic industry value chain, because it's very broad and very complex, and the different kind of companies they do a lot of different things. First of all, we have all the material and additive producers making the plastic raw material. In Europe, they are represented by Plastics Europe, amongst others. But here we have the really big chemical companies, but we also have smaller recyclers and material compounders. Secondly, we have companies distributing the plastic raw materials to our plastic converters. And also the plastic converters can be kind of divided in two parts. One of them are the companies that owns their own product, and they, in a sense, own this question. They can produce their own products and they are selling it. But also we have the suppliers working with contract manufacturing, and they don't have the same possibilities to affect the products they are producing. Instead, they are customers to a product owner who sets the rules and decides how a product should be designed and how it should be made. Second, last of all, we have the customers in the end asking for different kind of materials, but also sustainable material and sustainability use. So as you can see, the value chain is very broad. But of course, they all have the same common goal, and that is a sustainable plastic use. So I think we are very happy that the Swedish EPA and Osa Steinmark made this roadmap for us so that we can read that. And I think the whole plastic value chain really it can be behind that. It's very good. If we continue and see recycling or bio-based, well, that is really not a question. Of course, we want both of them. But if we look at the plastic industry today, a lot of focus is put on recycling. Both mechanical and chemical recycling is in focus. And one reason for this is that we have a lot of new EU policies pushing in this direction. It started with the European Plastic Strategy, followed by the Single-Use Plastic Directive, where we, for example, have this new recycled content of 30% from 2025. Also, mandatory recycled content is discussed within the Circular Economy Action Plan, for example, within whole packaging industry, but also in construction and automotive. Further on, we have this new membership fee, meaning that our member states, their fee to the European Union will partly be based on the quantity of non-recycled plastic packaging. This is sometimes misinterpreted as a tax. It's not. It's up to every member state to decide how they will finance this. But we have seen examples of European countries that will introduce a tax to cover for this. But once again, it's about recycling and recycled content. In Sweden, we are looking at introducing 30% recycled content in all packaging from 2030. And we are also talking about 75% weight of plastic material that should be recyclable. Then, of course, as mentioned here earlier today, we have a big problem with plastic pollution. And we need to start to recycle all the plastic material. It's just too valuable to go for incineration or end up in nature. We can also see that the product owners have started to ask for more recycled content in their product. If we continue talking about mandatory recycled content, the plastic material producers presented just a few weeks ago and say that they are welcoming the revision of the Packaging and Packaging Waste Directive. And they suggest that a target of 30% recycled plastic by 2030 should be included. But at the same time, they point out that chemical recycling will be crucial to reach this goal. The plastic converters represented by UPC, European Plastic Converters, said that, well, this is for sure reasonable, but responsibilities needs to be shared within the whole value chain of the plastic industry. So I think we will see a lot of discussions coming years regarding mandatory recycled content, starting with the PET, but more materials, or I say more applications will follow. And one big question or important consideration for the plastic industry when talking about mandatory recycled content is the points of what will be considered as recycled. Will pre-consumer material be included, or will it only be post-consumer material? We're in the process chain to measure, and how should we handle fillers? Many plastic materials contains up to 20-30% of mineral filler. How should that be taken into account? Also, we have complex products. Should we then look at the mass of the plastic, or should we look at the total weight of the plastic, or this complex product? Also, traceability and verification has to be sorted out because we can't measure recycled content. We could see that there might be some recycled content. It could be due to an odor or miscoloration, but how to measure it? I think here is a very important area for more research and investigations to find good ways to do this. Also, one can think of how should we put these demands on every single product, on a group of products, on the manufacturer, on a whole industry segment, or should we look at countries? For the PET bottles, we will look at countries, but maybe is that the best solution? How should we handle this? Also, there is a discussion between the balance between supply and demand. We see a risk that recycled material will only be transferred through one non-regulated product to a regulated product. This could, for example, happen to the PET bottles again, since the textile industry is using a lot of recycled PET. It might be that we are just moving recycled PET from textile industry back to the packaging industry. A question that's not been that much discussed is the connection or correlation between recycled content and recyclability, which need to be considered if we start to add high amounts of recycled material into our packaging, for example. And then, as Osa also I think mentioned before, we have some legislations and standards making this very hard, especially for food contact materials. But we can see it in other areas as well, for example, for the plastic piping industry. But I hope you haven't missed this, because big investments are being made in Sweden. We have Site Zero, where Svensk Plaståtervinning recently presented a huge investment in Motala, where the goal is to reach a recycling rate of 55% of all our packaging by 2025. And this is not just to introduce more techniques for sorting, it's also about working more with recyclability of the packaging that comes into this big site. Secondly, just before summer, Borealis announced that they, together with Stena Recycling, are investing in a big chemical recycling plant in Stenungsund based on the pyrolysis method. And also this is a good way to take care of the materials that we cannot mechanically recycle. Because mechanical recycling will always be the most efficient recycling method. But then we need a variety of different kinds of chemical recycling techniques to take care of the material that cannot be mechanically recycled. So what will the way forward will be then? Well, plastic will be a part of a circular, resource efficient and bio-based future. But focus should maybe be on sustainable material use, not focusing on individual material groups. We all know that plastics is heavily debated, and sometimes that leads to fast solutions to tackle just a symptom of a larger problem. So we should have an overall focus, talking about properties rather than material and origin. We should improve the recyclability by product design, but also in development in more efficient recycling techniques, both mechanically and chemically. And plastics are just too valuable to energy recover. Then, of course, we should continue to work on possibilities to repair and improve the lifetime of plastic products, and also look to the possibilities to use sustainable feedstocks. If you want to look more onto this, I can give you tips about the sustainable plastic strategy that was presented last year, where Plastics Europe, UPC, Suschem, Cefic, and others made a good report on how they see the plastic future. Well, that was my quick overview from the plastic industry, and I'm happy to ask any questions. And also, you have my contact details, and I really look forward and hope that we will conduct a good amount of nice research connecting to plastic recycling and sustainable plastic use in the future.
Tack så mycket. So you have a bunch of very important and timely questions regarding the challenges that you're facing. I was wondering about collaboration again on the European level, because you mentioned several challenges or questions that you have sort of designing for recyclability. But then you also represent a number of companies that are not only based in Sweden, but actually sell products on the European market. And then you have 20-something different recycling infrastructures and different labels to put on the packages that mean different things in different countries. So how can you work on the European level to sort of coordinate activities and make it easier for your membership companies to work on the European level?
That's a good question. I think we have very good things going on. I didn't mention Circular Plastics Alliance now, for example, but they are working, the whole industry together here to reach the goal of recycling 10 million tons of plastic by 2025. A lot of good work is being done there. And then, of course, UPC, together with Plastics Europe, is also working on these big questions, because I think this is questions that are so big that they need to be handled on the EU level. We can't start to have our own kind of policies here, because that will interfere with the free market also in Europe, and it will make consumers more. It will be hard to know what everything means, basically.
It's kind of hard as a consumer these days also to find and navigate your way when there are so many different labels that mean different things, and those words mean different things or can be interpreted. Like you mentioned, bio-based and recyclable, two different things, but it's easy to mix them up and so on.
Yes, I think bio-based and the term bioplastics it starts to make people confused as well, since you can talk about biodegradable or bio-based. Exactly. And there, I mean, not so. Yeah, it's a lot of work to be done here, I think.
Well, thank you for sharing those perspectives and the work that's going on within your organization. Thank you so much, Henrik. And I think also the next speaker has a lot to add when it comes to sustainable industries. And that's our next speaker, Dr. Thierro Chanstoft. He will come from the Swedish Agency for Innovation Systems. And you will tell us more about your activities in this area. Thank you.
Thank you so much. And let me see if I get the presentation going here. Are you able to see it now?
Not yet. Hang on a second.
There.
Yes,
How about
Thierro,
now?
now we can see it. Thank you.
Good. And let me just get started here. Yes, thank you so much for the invitation. And climate changes, growing population, and depletion of natural resources. We are facing great challenges, and we know that we need to transform our entire society, our cities, our welfare, our production, value chains, and consumption patterns into something sustainable. So business as usual is not an option. The severity of the situation is beginning to sink in on a global scale, and we have the first time a common language for sustainable development with 17 goals to strive for together. In order to achieve the goals, we need to promote innovation at different stages to transform entire systems and make the transition to a sustainable future. We need to create conditions for what we call system innovation. What role does Vinnova play as an innovation agency? We know that we need to take on a broader role, not only as a provider of funding, but as an agent of change, sharing our expertise. This can be a matter of identifying, mobilizing, and funding projects to reinforce Sweden's innovative capacity. Swedish industry has the potential to lead the transformation to a more sustainable and climate neutral industry, both within and outside the country's borders. Individual companies, but above all, large parts of value chains, can bring about the change that is necessary for us to stay within the planetary boundaries. Our focus is on production systems, mainly on the manufacturing and process industries. The question we are asking is how to produce responsive and smart factories, remanufacturing, industrial symbiosis, which increases circularity of materials, new processes like carbon-free steel, electrification, new fossil-free fuels. We have identified 4 impact goals for this area. Global competitiveness. The industry's global competitiveness is necessary for growth and welfare. Companies that export climate-smart technology and services contribute to the reduced emissions in home country and abroad. Second, climate neutral and circular production. We need to adjust material and energy flows to be use of renewable sources for both. Third, a socially sustainable industry. An attractive work climate creates the conditions for attracting cutting-edge skills. Increased collaboration between the industry and academia ensures the supply of skills. And fourth, resource efficient and resilient value chains. We need to reduce the need of resources, especially virgin raw materials, by use of automation, digitalization to reduce waste. We need to increase the portion of industrial symbiosis, where one's waste is the other's raw material. We must also increase traceability and the opportunity to see the climate impact at each individual level. Now, when it comes to polymers, this diagram says that there is more than 2.5 billion kronor spent on public funding since 2008. Almost half of it comes from the Swedish Research Council. When it comes to Horizon Europe, Louis Staffans at Formas has already mentioned it. The diagram also says that Vinnova has granted some 500 million kronor on polymer projects. However, looking more carefully, I can find some 300 projects worth for 1.7 billion kronor financed by Vinnova during the past 10 years. You can also see that the trend is slightly increasing and the size of project is going up. Here we can see the top 15 stakeholders. Number one with margin is RISE Research Institute of Sweden, with a total funding of some 300 million kronor. Surprisingly, number two on self-funding is University of Borås, doing research and testing on smart textiles and local production. Then comes KTH Chalmers with their broad portfolio of R&D projects, followed by large and medium-sized companies with niche applications. The largest Renewable program within polymer sciences is the Strategic Innovation Program of Bioinnovation. Many of the projects within that program are about replacing fossil-based products with bio-based. Next on the list is Strategic Innovation Program for Graphene, enhancing the physical properties of polymers. Third is the International SME Program within polymer technology through the Eureka network. Now, just to give you a flavor of projects Vinnova is funding, I will briefly present you a couple of them. This challenge-driven innovation project will increase the circular use of industrial, commercial and transport plastic packing through so-called closed loops. The Swedish Environmental Research Institute is developing and testing 3 different types of plastics packing, out of which one is of big bags and one of EPS packing. Volvo Cars has recently announced a strategy on recycled plastics within the target of 25% recycled plastics in all cars that are introduced from 2025 and onwards. This Vehicle Research and Innovation FFI project aims to work with the questions like how to recycle production waste, which recycling methods to use, alternative bio-based materials, and design for recycling like easy-to-separate solutions. Now you know that thermoplastics are widely used within the automotive industry due to their better recyclability. However, this project will develop a new graphene-enhanced thermoplastic material for aerospace applications. The aim is to significantly improve strength and to introduce electric conductivity via the graphene enhancement of the polymer for 3D printing applications. Materials with such a multifunctional capability enables disruptive techniques for integration of thermal management, electronics, antennas, and sensors. The purpose of this Eureka project is to develop an electrically conductive polymer-based material which is conductive enough to be used to make electrodes for EDM, that is electric discharge machining. Electrodes can be 3D printed with additive manufacturing, giving design freedom to form makers for injection molding. The result of this project will also be to cut the form production costs by 30% and lead time by about 40% compared to machining. Spin-off effects of developing a conductive 3D material of this caliber are significant, with applications like radio frequency and electromagnetic shielding, anti-static protection, circuit boards, and sensors, for example, for IoT applications. So with that, I thank you for your time. Thank you.
Tack, Thierro. Very interesting. You show some really interesting projects here. I find something they have in common. They're quite advanced in terms of technology readiness levels. Is that, you would say, criteria for projects within the Vinnova funding system, that it has to be a certain maturity?
That is correct. So most of the projects Vinnova is funding, they are collaborative projects. That means that the industry is usually on the driver's seat and the researchers from universities and research institutes, they are solving the problem on a more holistic level. So the industry-driven project, that is kind of Vinnova scope on that.
So excellent opportunities to collaborate with industry and institutes then.
Definitely, and just to give you a hint about calls we have, so we have, at the moment, we have one call for planning contribution for Horizon, and also planning contribution for new competence centers. So maybe in the near future, we have a competence center within polymer technology. So you're welcome to join that call.
Thank you, Thierro. And thank you for mentioning the Competence Center, because tomorrow, when this conference continues, we will hear from Annette Larsson and the Fiber Competence Center that is funded by Vinnova. So it's an excellent example of what you're just talking about. Thank you so much.
You're so welcome. Thank you.
So are there questions to Thierro or any of the speakers of the first part of this afternoon's session? I hear that there's nothing in the chat for now. No? Well, if not, thank you for hanging in there so far. So it's time for an intermission. So wherever you are, please know that we will be back here by 2:45. We'll be back then.
Okay, welcome back, all of you, after the coffee break. And so far we have been listening to the different funding agencies in Sweden, and also something about the Swedish perspective of the plastic pact, I would say. And now it is mostly the researchers who are going to present, and we have the pleasure to start with a French speaker, Luc Avereux, who's an expert in polymer chemistry, polymer technology, including bio-based. And he's going to speak about renewable polyurethanes from cradle to cradle. Welcome. It's nice to see you.
I want also to thank the organizing committee for this invitation. So, and good afternoon to all of you. It's also a pleasure to see only some very good friends from Sweden or France. So, as you mentioned, my talk today will be much more focused on science, with specific detail linked to my research activity in Strasbourg, where we develop a research activity in connection with different industrial partners. So my talk today will be on polyurethane with a circular bioeconomy approach. So as everybody knows, polyurethane since 1937 with Otto Bayer is obtained by reaction between polyol and polyisocyanate. So polyaddition, it's a very fast and exothermic reaction. So we obtain a urethane group that could be done in one shot. So we mix together the different ingredients. For example, in the case of foams, or also in a two-step approach, you can, for example, develop elastomer like TPU. Most of time also, in the case of polyurethane, we use a lot of additive, could be different catalysts and so on. So usually the formulation to develop polyurethane are very, very complex. So polyurethane is considered as the fifth polymer family with a worldwide production of around 20 million tons. So it's mainly based on foams, could be soft foam based on open cells, or rigid forms, mainly for insulation with closed cells. But you can find different other applications, for example, on coating, elastomer, adhesive, and also on biomedical. So we can develop a different type of thermoset and thermoplastic architecture. So to improve the life cycle analysis of polyurethane, you can develop a different approach. for example, you can develop a bio-based polymer chain. So in Strasbourg, we work a lot on this topic. So we have used different biomass, and we have obtained different kind of macromolecular architecture. Well, I don't want into the detail of all the different bio-based polyethylene that we have developed. My talk today will be only focused on one very simple example. For example, the case of the lignin. Lignin is mainly obtained from wood. So lignin is a very interesting building blocks because it's a polyol. And present different hydroxyl group. That could be phenolic and aliphatic. You can find a different lignin according to the fractionation process and according to the type of resource. Unfortunately, the OH, the hydroxyl group which are present on lignin, present quite low reactivity and quite low accessibility. So lignin must be modified to obtain active macropolyol in order to obtain after a different polyol chain. For example, from lignin, you can do what is called ring opening polymerization with epsilon caprolactone or propylene oxide. It's called oxyalkylation. And you can also combine lignin with fatty acid. In this case, you can work, for example, on oleic acid, which is a very common fatty acid. And then you can combine both types of resource, so oleic acid, mainly obtained from vegetable oil, and lignin, which is mainly obtained from wood. And then you can develop a different reaction. For example, in the first case, you can do the chloration of the oleic acid in order to improve the reactivity. In order to obtain a esterified lignin, so you obtain lignin with a different branch and double bond. And then from the double bond, you can develop oxyurane, epoxy groups, and then you can open the epoxy group with methanol in order to obtain IVN, secondary hydroxy group. So you obtain an active macropolyol, and then you can do the reaction with polyisocyanate. So this approach has been developed with my main industrial partner, which is Suprema, is a worldwide leader on building insulation. And with Suprema, we developed some years ago joint research lab, which is called Mutaxio. So last year, we developed a ton production of polyethylene foam from this aromatic polyol. And it was a successful story, but a very long story because we started the research in 2010 and we have obtained the industrialization of this product only last year. So we need 10 years from the white page to the final project. Another example that I want to show you is the case of PU with high recyclability. In this context, we develop a bio-based covalent adaptable network. If you compare thermoplastic and thermoset, you can see here that thermoplastic presents a very high recyclability, but compared to the thermoset, quite low mechanical properties. That's why people have developed another type of material, which is called covalent adaptable network, which is based on reversible covalent bond. You can find, for example, vitriners and different type of material in this field. And this type of network presents the double advantage. So they present high mechanical properties and also a very nice reprocessability, as I can show you. We develop a covalent adaptable network with DXL direction. So you can do the reaction between a gen, in this case a furan, and a genophil, a malimide. And for example, at 60 degrees, you can obtain the reaction between both compounds. And if you increase the temperature now from 60 to 120 degrees, you obtain the retro DXL direction. So you obtain the dissociation of both compounds again. So you can play on the temperature to develop the properties of the material. So starting from different fatty acids, we have performed the functionalization with furan and molyamine group in order to obtain reversible covalent network based on polyurethane architecture. So just to show you some property of this material, if you start from example with a solution at the room temperature, and if you increase the temperature, so you obtain a gel, as you can see here, at 65 degrees, and then if you increase again the temperature at 120 degrees, you obtain the retro SR direction, and you obtain the liquid again. And then if you cool down now till 65 degrees, you obtain a gel. So you have a reaction which is reversible according to the temperature. That is very interesting. This material presents also a very nice recyclability. So you can develop different cycles of processability. And you can see here that after each cycle, we are able to preserve the mechanical property of this material. So this material presents a quite nice recyclability and also present other type of properties like, for example, self-healing. For example, you're starting from a dumbbell sample, you can cut in half here, and then with heat treatment, the integrity is recovered. That is also a very interesting property, self-healing. So this material presents different properties, very interesting, and then you can develop a different application, for example, to increase the lifetime of the materials. And also, it could be interesting to ease the deconstruction at the end of life of the materials. Another example in order to improve these materials is to decrease the toxicity, because isocyanate is very well known because it's a toxic product with a carcinogenic impact. So you can develop, for example, bio-based polyurethane without isocyanate, which is called non-isocyanate polyurethane. So you can use a reaction, in this case, between a cyclocarbonate and amine. So, for example, you can start from sebacic acid and glycerol, which are bio-based products, and then at the end, you obtain a bicyclocarbonate with two cyclocarbonate at the end of the molecule. And then you can perform the reaction between this bicyclocarbonate and polyamine with control functionality. And at the end, you obtain a non-isocyanate polyurethane, in fact, an hydroxyurethane. So you can see here the hydroxy group and the urethane group here. But unfortunately, compared to the very conventional polyurethane, this type of PU presents quite low molar mass and quite low kinetic. So this kind of product can be used only on very specific application, for example, on adhesive application, but no more till now. Just, I want to finish my presentation to give you an example, because some years ago we have developed a global chem biotech approach from cradle to cradle. This approach has been developed in the frame of different European projects, a past project before SB, H2020, and two other projects, My Place and Mix Up. In the frame of this different European project, we have developed a biorecycling on polyurethane. So we have developed a control enzymatic degradation. For example, with a specific enzyme, you can break the ester linkage that you can find on the backbone of the PU. And even we have been able to show that you can cut the urethane linkage combining different type of enzyme, in this case, amidase and lipase. In the last step of this project, we have developed a circular chem biotech approach. So in this case, starting from, for example, polyurethane foam at the end of life, we have performed the deconstruction using biotechnology with enzyme. And in this case, we have preserved the urethane bonds. So we have obtained building blocks with different group, like for example, hydroxy group or acid group. And then from these different molecules, we have been able to do polymerization in order to obtain a second generation of polymer, in this case, a thermoplastic polyethylene. But you can imagine another cycle, so starting from this polyethylene to obtain another polyethylene. So we are in this case, in the case of circular and also bioeconomy, circular economy and bioeconomy. Just to conclude my presentation, so we have been able to correct different issues linked to the polyethylene, highly versatile polymer, to obtain greener and renewable polyethylene with quite low toxicity, recyclability in the frame of what is called circular bioeconomy. So more recently, so we have developed a biorecycling approach, which was based on controlled enzymatic degradation. I am sure that Sophie tomorrow will present more detail on this approach based on another type of polymer. So this approach is a new and promising approach for PU at the end of life with a sustainable and circular development. Just to end my presentation, I want to invite you, if you have the opportunity in Strasbourg, for example, to test different bio-based liquids, beer or white wine, and so on. So it's time now if you have some questions. Thank you for your attention.
Thank you very much. Thank you very much for these fascinating examples. I'm wondering, in the last case, do you have any interest from the industry who wants to do this recycling?
Yeah, of course. We have a different industrial partner. So we have developed 10 years ago a joint research lab with a big player on polyethylene in Europe, which is called Suprema, mainly focus on insulation materials. And they are very, very interested by this approach. Very.
Yeah, absolutely. That's really great. And moreover, going from thermosets to thermoplastics also is a big step for you.
Yeah. I agree.
Yeah, and a good use of lignin, I think, also is very interesting in this case. Absolutely. Congratulations for these successes. I'm wondering if any of you have any questions for Luc about the polyurethanes. Yes?
Yes, I have a question. I don't know if you can hear me speaking without a microphone, but yeah, you can. Thank you. I was just curious. So whenever you process lignin or lignin adducts, you usually get something brownish, yellowish, as you can see also in your sample specimens. Is there a way around that color?
No. In fact, it depends on the size of the oligomer that you use. But you use well, it's a little bit coffee. It's very similar to coffee powder at the beginning of lignin. You're right. But when you integrate lignin inside the macromolecular polymer, you lose the color. You lost the color.
That's right, yeah. And moreover, if it is not seen, if it is an adhesive, perhaps the color does not matter too much. But if it is a coating, maybe it does make a difference.
Well, in the picture, you can see the color of the foam, but it's a little bit yellow, no more.
Okay, cool. It'll be interesting to follow up your research in this area. It's very fascinating. Yeah, thank you for joining. Thank you for joining, and I hope you will continue to listen to the other talks.
Okay.
Okay, we go on to the next speaker, and that is also online. That's Maria Pentelay. Has Maria joined the meeting? And Maria is a research professor in VTT in Finland, and she's also she's adjunct professor in Aalto University in Finland, and she's a very well-known researcher in the area of industrial biotechnology and synthetic biology, and her expertise is in these areas for the production of fuels, chemicals, materials, etc., using microorganisms, especially fungi. Maria, it's good to see you here. Can you hear us?
Yes, I'm here. I have been here.
Yeah, nice to see you. And Maria will speak about production of copolymers in yeast. Every time I listen to you, you have something new to say, Maria. So welcome.
Let's see. Very nice. It's good to be here, and I'm talking about biotechnology, but of course I'm coming from VTT, from the Technical Research Center of Finland, and obviously we do a lot of, let's say, materials and plastics related work, also recycling of plastics. But my topic is biotechnology, and actually a certain narrow aspects of that. So at VTT, we have quite some platforms for developing biotechnical solutions. So we have organism development through synthetic biology platforms. We have also organism selection, screening platforms, high throughput screening platforms, and then platforms for process development, like various different scales of bioreactors, and then scale up and piloting and raw material processing for the processes. But my focus then today is think about the small organic acids, small monomers for polymer production, and I will concentrate a few of those. We have been working on others as well, but a few of those, which are lactic acid, glycolic acid, and 3-hydroxybutyrate, which is a precursor for PHB. And if we think about biotechnical routes, so of course the whole idea is that we can use renewable raw materials. Here is glucose depicted. You have a cell, and the most common case is that you use the raw material then to produce the acid monomer, and then you polymerize that with chemical technologies. And another concept is, and which the microbes are capable of doing, is to take the glucose in, produce acid inside the cell, or convert that, then polymerize in vivo directly to the polymer, and then you extract the polymer out from the cells. And this, of course, is a nice concept of reduction of process steps in polymer production. And if you have the acids available, of course, you can then think about that you could feed them to microbes, and they could do the polymerization, and then you extract thereafter. And when doing this, so of course that demands quite a lot for the microbes, because they need to really be low pH tolerant. They need to tolerate the stress in production and in the conditions. And this is why we have been concentrating on various different yeasts, not just the baker's yeast, Saccharomyces, but also very many other species. And I go back to this case, which is lactic acid for PLA. This is very well known, and we worked already years back with Cargill Dow NatureWorks to make this process, but this is a good example. So they wanted to actually replace lactic acid bacteria in the process, because they thought that there should be a more acid-tolerant production organism metabolism, and also such which would require minimal nutrients. And that is why we then developed for them a yeast-based process. There are lots of benefits in the process cost because you can avoid, for instance, gypsum salt formation in the purification step. And this process has been several years already in industrial production. The titers are very high, and also the yields. You can see here the biochemical pathways, so glucose directly you can pull it down to lactic acid. You sort of minimally block ethanol formation. But of course, you do a lot of other things also, engineer the cells. But in principle, it is quite straightforward. We know it can be produced from xylose, and we studied various yeasts. So this is a ready-made process. But very much the processes are based on starch materials, sort of pure sugars, and thus, for instance, we have every now and then we have some like second generation raw materials or other types of waste fractions available. Then take lactic acid production as an example. And recently we have studied more molasses, and that is for the reason that there is a Finnish company, Finfoam, who got access to leftovers from soya production. So it's soya molasses now here. We are then wanting to convert into PLA. And what they would think of using that is actually for thermal insulation materials in buildings. And they aim for a production plant, or let's say demo type of a pilot or demo scale production plant in 2023. And there's lots of stuff, of course, in soya molasses, but what is also interesting is that there are special carbohydrates in that in quite big amounts. So lots of galactose containing raffinose type of sugars. And in order, of course, to have a high yield from the raw material, the yeast should be able to ferment all these, which it cannot do naturally. And thus you need a lot of enzymes like alpha galactosidases, which can cleave here between the galactose units, and then inverters, which can cleave this linkage here. And with that, you would then end up in a mixture of monomeric sugars, and this would be then available for the yeast. And what was done then was to study alpha galactosidases, take the best ones, make the yeast to secrete these enzymes to the medium. Then, of course, we needed to put the lactate dehydrogenase gene into yeast to get the pyruvate to lactate conversion, and then block ethanol formation, and thus get from galactose, glucose, and fructose now the pathways towards lactic acid. And it succeeded actually pretty well. So after optimization, over 100 grams per liter lactic acid was obtained from soy molasses. And also this good productivity was retained when one went to pilot scale. So, not to the big pilot scale, but 1,000 liters. And this was very good. And the material was then purified and polymerized. And I'm really happy because this, I think, opens up the thinking that even polymer monomers, precursors, could be produced from waste fractions. So if lactic acid can, so probably many, many other acids. So this is a good demonstration case. Another case I would like to bring up is glycolic acid. And this is a 3-carbon acid. And for the reason that if you look here the properties of polyglycolic acid, PGA, and compare that to PLA, you can see that it has some favorable properties like the water retention property, the oxygen transfer rate is very low. So thus it makes could make a much better barrier material than PLA is at the moment. And you can see that it could, or it's predicted that it could sort of replace 30%, for instance, of current EVO use. One could replace by PGI. And also one could make copolymers with lactic acid, and these could have uses in medical applications, for instance. But the interesting and challenging thing actually was that it was really difficult, has been really difficult to produce that from glucose, glycolic acid. It can be easily produced from ethanol, but not directly from glucose. And I don't go into details, but it's just showing here that this is the normal route in the metabolism, glucose to the glycosylate cycle, and then you do some genetic modifications and get glycolic acid in principle out. And we studied a lot, glucose repression, all kinds of things. Why was this not occurring? But finally, then we have had a solution where we have this glycosylate cycle working at the same time than the oxaloacetate pathway in yeast. So you have two routes towards glycolic acid. And now the production levels are sort of 15 grams per liter, which is not yet much, but still it's promising. You can think about that you could get then further to industrial scale, just to show how complex the genetic engineering can also be. I will then now jump to the third case I have, which is then production in vivo in the cells, copolymers. And this is a sorry for my so this is a picture from a bacterium which is actually filled with PHB polymers, and the bacterium or strains in general, they produce it from hydroxybutyrate acetyl-CoA precursors with the synthase enzyme, which makes the polymer. And analogous now, of course, you could then think about that you would have lactic acid or glycolic acid. You would make the corresponding CoA derivatives here, and then you could make the polymers or the copolymers. And much of these enzymes are same or similar enzymes which you can use here in the polymerization. And this is then what we went on doing. So here shown how from glucose we introduced a pathway in yeast now to make PHB, which is a biodegradable bioplastic. And then also we introduced the pathway of making D-lactic acid, and thereon the acetyl-CoA derivatives, so that we could make either polylactic acid or then a copolymer with the PHB, with the butyric acid. And here you can see that if we only had a strain which had this pathway here for PHB, so you have, when you extract the polymer and then analyze the monomer composition, you have 3-HB there. But if you have a strain where you have also the lactic acid pathway, so you then have both of the monomers produced. And with this result, we then thought that it would be nice actually to be able to control the monomer proportion in the polymer made in vivo, inside the cells. And what we did was then to design a sort of synthetic expression cassette, where you have a regulatory factor which binds to a synthetic promoter, which then turns on the gene. In this case, we wanted to control the lactic acid production. And then this binding of the transcription factor can be controlled by adding to the medium doxycycline. So the more you have doxycycline, the more you have the transcription factors binding to the promoter, and the higher the expression of the gene of interest. And you can see it here if one looks at the lactic acid in the medium. So the more doxycycline there is, the higher levels of lactic acid are now accumulating into the medium. But when you then have and put the system into the strain where you have both the PHB and the PLA pathways, and look how copolymers would be formed. So just to show here very quickly, so the more you have doxycycline in the medium, the higher the lactic acid proportion in the polymer when you isolate that from the cells, so from 15 to 23%. You can also increase the polymer amount there, and we have analyzed with NMR they are really true copolymers and not just PLA and PHB produced separately. So this is a good example how you can tune the proportions. You do not need to use doxycycline later on. You can then use synthetic promoters to fix the expression levels and get the wanted proportion of the monomers in the polymer. So I would like to sort of then conclude in a way that just with these three different monomer cases, one could say that there are lots of possibilities to tune the polymer properties. And obviously then there are lots of other monomers which you could then now bring in and start sort of plucking and playing and creating novel polymer properties to replace the fossil plastics. We are also at VTT working on other things than bioplastics. We're working on making carbohydrates in vitro or with cells, silk, also mycelium leather. And by combining these different types of polymeric materials, we can then make composite structures like tooth implants. It's a recent case which we have made by combining biosynthetically made composite materials. So thank you. I hope I wasn't too long in my talk.
Well, thank you, Maria, and thank you for showing so nicely how biology can be used in a nice way to make bio-based plastics and very novel structures too. I have a couple of quick questions for you. I mean, you work a lot together with the industry. So how long are your project timings? Well, let's say when you start from, let's say, designing a pathway and finally you talk about 100 gram per liter production, and then it already is in the industry. What are the timelines here?
Let's say that this making the lactic acid from soya molasses, where there was enzyme screening, there was engineering of the cells. So I would think that the cell engineering didn't take, let's say, more than a year. But then, of course, the process optimization, purification, and so on, that took a longer time. So it was probably 3 to 4 year project, what we had. Then, obviously, in the early days when we started with Cargill Dow, so the projects were very large, and I think we worked with 6 years with them at the time. But Of course, the proof of concept can be probably obtained quite quickly. And if we think about that, we have now all the modeling and all the sort of gene assembly and robotics ways to screen for the strains. But then the optimization and, of course, the process development. So I would think that they would still take, let's say, 3 to 5 years time, that you would get to such level that you can start really then scaling up. But it depends, of course, completely how much there is prior knowledge and so on.
Yeah. And do you think the copolymer that you're making, does that have any added property to it in terms of mechanical or thermal properties more than the individual polymers?
Yes, of course, you can tune then the sort of flexibility and moldability and so on, and the mechanical properties. We haven't studied all the variants, but of course that's already I think known also from let's say just chemical polymerization, that you can tune the properties. So yes, for sure. I mean, there are differences in the properties, and even just the interest of, let's say, glycolic acid and lactic acid copolymer is there, that you can really tune the properties. And then, of course, biodegradability and things like that may also come to the picture.
Yeah. I had a few more questions, but I think in the interest of time, it may be good to go on. I don't know if there are any questions in the chat. No? Okay. Thanks, Maria, but maybe some questions may come later. Okay. Thanks for the wonderful examples that you have shown today. And see you again. Okay, now we have somebody in person. And so besides going bio-based, polymer design is something that is important for enhancing the recyclability of polymers. And that is what we will hear from our next speaker, Karine Odelius. She's just from here, local, Stockholm. So it's good to see you here in person, and I'll leave the word to you.
Well, thank you very much, and thank you all organizers for inviting me here. It is very nice to be in person speaking, I must say. Yes, so my name is Karine Odelius, and I'm from KTH Royal Institute of Technology, and specifically from the Department of Fiber and Polymer Technology. But today what I'll talk about is the work that we're doing at the Division of Polymer Technology, so I'm sort of narrowing it down to some extent. And the division is headed by Professor Minna Hakkarainen, who is here in the audience. We have also Professor Ulrika Edlund, who is also here in the audience. And we have Professor Anna Wistrand, and also then me, we're the faculty. And then, of course, there's postdocs and PhD students and researchers working with us. I want to start by showing an image that I know that we've seen many times before, just to sort of highlight the way we look at plastic production. So today we have a linear plastic economy. We were looking at it mainly a fossil-based resource, and we're producing waste, and this is for the packaging applications. And this waste is leaked, it's landfilled, or it's incinerated. Very little is in the closed-loop recycling scheme. So we're talking about 2% within this closed loop. So a lot of our research is within this field, looking at new bio-based resources and also in closing the loop on plastic materials. And how do we approach this? Well, what we do know is this, that we have thermoplastics being formed, and this is the proportion of the different thermoplastics that we do see in the world, in the global production today. And a lot of that is carbon-carbon backboned plastics. And for each of this type of category, we need to sort of optimize a recycling scheme to ensure that we can have methods to make recycling viable. And in this carbon-carbon backbone, we cannot go back to the original monomer. We need to find new material valorization techniques. And I'll tell you a bit about the work that we're doing within this field. If you have a functionality in the backbone, which we have seen already today, you have the possibility to chemically recycle back to monomer. And PET is a commercial example of that. But the question we always ask ourselves is then, is that feasible environmentally and energetically? What does it demand? But then we also have the category of other that hides a whole bunch of different things. And I'll show you some examples where we're trying to design new polymers in the other category. And like what Professor Averot talked about earlier, we have also the category of thermostats. That's not even included in the production volumes that we're seeing. And how do we do this today, and what can we do for the future? This is also something I'll mention today. So we look at many different aspects of this, and what I'll talk about is sustainable building blocks from renewable resources, what we do with this, both in the polymer range, biopolymers, but also in monomeric structures. I'll give you some of our examples on covalently adaptable networks. We look at imine chemistry, disulfide exchange chemistry, and other chemistries as well. I'll talk a bit about microwave-assisted methodologies that we're looking into for material valorization, and in this case, some examples of commodity applications, and then also the design for chemical recycling work that we are performing. So to start off with the sustainable building blocks, this is work that Professor Ulrika Edlund contributes with. Where she's looking at a biomass that's from agriculture, from wood, or from algae, looking at a binary refinery concept here to try to maximize all the different fractions from this biomass. A lot of the work is also on trying to make these processes as green as possible, so recycling extraction media such as water and such, to really optimize the products that she's gaining. Then there's synthesis and modification and functionalization of these polymers, generating materials that can be produced into different devices. And some examples are shown as well. And of course, in a very important aspect of this is what happens at the end of life of these devices. How should they be handled? Can they be recycled? Are they degraded? Should they be degraded? And what are the aspects of that? This is, of course, all based on an important characterization platform that is needed for each and every of these steps to really maximize this. And also looking at a characterization platform and developing new techniques where you can characterize the saccharides, for example, within the biomass from the beginning to ensure that you know what you have and how to valorize that in the end. Then there's a plethora of different materials that have been produced from these polysaccharides, for example, all within sustainable development, I'd say. Composites, adsorbing and absorbing hydrogels for wastewater treatment, bioplastics for use, and magnetic microgels, for example, just to name a few of the different products or possible future products that are being formed. So this is in the biopolymer field. We also do work with you looking at bio-based building blocks, and in this case we're looking at covalently adaptable networks. This is a bio-based building block. It's ethylene brazylate. It's originating from a fatty acid. It's a diester, so it can be used to create various different linear polymers, but also networks. And in this case we're using disulfide exchange chemistry. Oh, it's not showing up. I'll point like this then. Using diamides and triamides to create networks. So polyethylene, polyamide type networks with exchangeable bonds that can be reprocessed into new materials in numerous cycles. What I'm just showing here is that even at 3 different cycles, we retain the properties. And the properties are varied depending on the composition of the network. And this can be extended to other types of functionalities as well within the backbone, so not just amide chemistry. Another example is looking at imine type of chemistry. In this case, we're working with vanillin as a building block, coupling it to a precursor that has an exchangeable imine bond that can be UV polymerized into various different shapes and forms. Again, we can reprocess it by just grinding and melt pressing it again, and can also be chemically recycled by dissolution. So it's a plethora of different chemistries that can be performed within this network or framework of covalently adaptable networks that were discussed earlier as well. Within the area of material valorization, I'm not going to go through all the examples, of course, but we look into different commodity applications and also complex type of waste. So I'll give you an example of polyethylene and the work we've been doing there, but we've also looked into PET and the polyamide polypropylene rug, trying to valorize all of the different materials and creating, by microwave-assisted reactions, various precursors or chemicals that can be used for a long range of different applications as well. So if we focus on these, the container and the plastic bag, they are made of polyethylene. The bag from low-density polyethylene and the container is a high-density polyethylene product. It can be microwave valorized into an assortment of different diacids and monoacids. And the composition of this can be tailored by time, temperature, and acid concentration. If we then look at the products made by high-density polyethylene valorization, these difunctional acids, they can be polymerized directly as the product formed with a diol, creating polyester oligomers that can be used to covalently graft into a polymer as a plasticizer. In this case, we used PLA as a model. And I'll just show you some of the results here, where we can see that if we graft this plasticizer onto the polylactide model, whoops, nope, pointer, I'll go point here. We see a long elongation increase, meaning that we are plasticizing this polymer. And then we still retain this recyclability or the degradability of the PLA as we have an ester backbone again. In the area of designing for chemical recycling, we're looking into the heterocyclic rings or cycles. These are considered to be a promising alternative for the future, as we can go push the reaction towards the polymer side, but you can also push the reaction back to the monomer side, making this actually energetically possible or feasible. We're dividing them into thermodynamically disfavored monomers and thermodynamically favored monomers. And in this case, the disfavored monomers tend to want to be in the monomer form, whereas the favored ones tend to want to be in the polymer form. So why is that important? Well, it's important if you want to make a polymer, of course, that you can create the polymer. But it's also important during processing, because if you have something that tends to dissociate back into its ring form during processing, then it's not much use in an industrial setting, right? So what we wanted to do was to combine this, but still retain the chemical recyclability. So what we did was we did a quite easy setup. It's in bulk. There's organic catalyst, there's no solvent, and then after a certain time frame, we have a polymer. If we then increase the temperature, we want to mimic processing or chemical recycling. So what happens? Well, to make this feasible, we first needed to look at the kinetics of the reaction. So what happens if we co-polymerize these different disfavored and favored monomers? Well, if we look at NMR and see where are the more monomers incorporated, which becomes very important, we can see that for the delta decalactone and epsilon caprolactone system, in this gray area, which is the polymerization part, they're incorporated at the end of the polymerization. This means that they're sort of protecting our polymer during processing or chemical recycling. Whereas in the other case, they're situated throughout the polymer, meaning that if we elevate the temperature and try to form this polymer into something, then it'll be chemically recycled automatically. But then if we end cap it and we save it from chemical recycling, we need to be able to induce chemical recycling as well. So if we look at, this is a busy table, I just want to show you. Catalyst is an important aspect of this. Where organic catalyst such as DPP is shown to be forming more cyclic monomer, which is where we want to end up, back where we started. We don't want to make the acids, we want to make the cyclic monomers again. And then if we look at amount of nucleophile that we use to cut the chain, so we need something that initiates this, a lower amount of this actually creates a larger possibility for chemical recycling. So this is a means to design your polymer system to create the possibility of a future chemical recycling. So with that, I hope that I've shown you some of the work that we do within in the division, and a picture that has a few years on it now, but it's been a bit difficult to take neat pictures. So thank you for that.
Thank you. Impressive. Wow. You have thought of everything, looks like.
Yeah, well, I'm not part of all of it, I must say.
I just heard that Vinnova guy say, that, what was his name, Thierro, saying that a lot of money has gone into polymer research. I hope you have received some of that.
Well, yeah, it's a successful division, yeah.
But with all these nice examples, do you have industrial collaborations?
Yes, we do have, of course, industrial collaborations, yes.
Yeah, and anything that you think is going into the pipeline for the market, you think?
Well, there's of course always that wish, but I cannot speak for everyone within the division.
No.
I can, but I do foresee a good future for all of it. I hope.
True.
Yeah.
No, especially I find this chemically recyclable, the kind of those polymers, extremely interesting.
Yeah.
Where you just change the conditions and you get the, you can go into monomers and polymers. Any polymer question? Yes.
You mentioned at the beginning of your talk that when you have a CC backbone, then it's not possible to have the monomers, but I can remember that normally polystyrene and PMMA that are carbon-carbon polymers.
Good, you got me. Yeah, so yes, definitely PMMA is definitely you can go back via chemical recycling. I was oversimplifying it, I confess, yes, you're correct. But for the big, large groups, the polyethylene, the polypropylene, it's not kinetically possible. But I agree with you, yeah. So I apologize.
Yeah. We are running after behind time now, but are there any questions over the chat? No. Okay. But we'll catch you up in the break then. Thanks a lot, Karine. Really nice. And then we have the last speaker for this session online, Francois Gerard. Good afternoon. Yes. You're welcome to this conference, and he will talk about plastics of yesterday and tomorrow with regard to the circular economy. We look forward to hearing your presentation.
So, thank you very much for inviting me to give this talk to this kind of workshop or conference and in Stockholm. Unfortunately, and please apologize because I needed to stay in France because you know that last year it was the 1 century anniversary of polymers, but also the 5th anniversary of the French Polymer Society. And this Polymer Society has each year a special event dedicated to young scientists. And the young scientist event for the 15th anniversary take place today. And I needed to be there for that special event. So I just want to say a few words about what we are doing in my lab and how we deal with the polymer, and especially in regards to the circular economy. And then at the end, I will try to keep time for a special project, a special strategy, which is on the way in France, which is especially dedicated to the recycling, recyclability, and reuse of materials, including polymers, including plastics. So first of all, I just want to present my institution and my lab where I'm working. This is a lab mainly located in Lyon and Saint-Étienne in France, belonging from the CNRS and several universities. And we are about 200 members with less than 100 permanent staff and more than 100 PhD students as PhD student or postdocs. Mainly, most of them are paid by the industry under contracts. So we have research which is strongly related to basic research, of course, but dedicated to special application and in connection with the industries. So we are going from the polymer chemistry, from the molecules to the final polymers, including the processing step, which is a very important fact because we need to combine, and as we design a polymer, to take into account this special step, which is the processing, and also the application, of course, but also back to the monomer. And what we are doing is very close to what Professor Odelius explained just before, and exactly the same, trying to design the polymer as more relevant as they could be, and thinking about what we are doing with those polymers. And one special thing we install about one year and a half before is to have an interdisciplinary team on bioplastics, on recycling, on recyclability, on life cycle analysis, and joining several teams in social and human science group in other labs in order to take into account these new needs of including all the aspects for designing polymer on the most relevant way according to the circular economy. So that's why I will try to explain with example from our lab. So I suppose that also the slides will be shared, so I will not explain all the content of those slides. So our purpose is that we are sure, and you are sure now, I'm sure, with all the presentation of the afternoon, that the polymer could really fit the circular economy requirement and also being able to respond to the social need at the same time. So we are really in now, as scientists, we have in mind this circular economy requirement for designing new polymers or considering the polymers of yesterday, from yesterday, to be included in this circular economy. So what we are doing could be shared in 5 different axes. The first is to be reusable, or I will detail each of those ones, to be reusable as they are, or in different types, or in other use, or in other natures. It could be we need to redesign the polymer in order to fit this circular economy requirement from using, for example, renewable resources-based building blocks, integrating end-of-life stages, as explained before, and also taking into account all the life cycle analysis. But also rethink about their formulation and shaping process, response to specific use, and also being able to repair or self-repair. So I will try to give example of what we are doing in each of those axes. So for example, be reusable. I just take example of what we are doing on PET, for example. We are working on PET recycling and the usual mechanical recycling. So and especially how to deal with the solid state polymerization step, which is one of the steps of this recycling process. But also looking to the chemical recycling of PET. So, for example, we are looking to the depolymerization of the catalytic process for depolymerizing this PET at low temperature and especially of polluted, about the mistake, of polluted PET. So being able to depolymerize even the PET which contains some contaminants, because the issue is not really to recycle the pristine polymers, the pristine materials, is to use them, is to consider them as they are in wastes. And we are also working on chemical recycling with upgrading the what we are obtaining from recycling process as high value monomers for example, preparing thermostable polymers. We can redesign the polymer also. For example, I took exactly the same example as PET. So as PET, we are working on the use of other biosource monomers as isosorbide or furane-based monomers in order to prepare PET-like polymers, having the same behavior and having the same ability to be processed. That's a very important fact in order to prepare fibers or bottles. And also, so that's a whole research, a complete research from the basic of the condensation reaction to the processing step and to the final properties, including also the recyclability. The important thing is also, as explained before, to redesign polymers to be more circular and to fit more the whole process. And we are working a lot on natural polymers, so biopolymers, especially polysaccharide-based materials as cellulose-based, guar gum, or chitosan, but also the use of proteins as a basis for materials, especially the proteins of the casein protein, and which could be modified or little bit or processed in such a way so that it's a mixture of chemistry, physical chemistry, and processing technique, rheology, and things to process such a casein in order to substitute some thermoplastic to buy a casein thermoplastic-based systems. And we create a company which is named Lacteps, with now about 60 staffs in them. So the important thing is also to redesign polymers as always additives, or to substitute those additives, creating some troubles for health from regulation for environment, but also as contaminant for recycling, to use natural based or bio-based additives as essential oil, lignin, and things we already see. And of course, to design, formulate, process more environmentally friendly polymer. And we call that way to design polymer and to the safe and sustainable polymer by design, as explained before, already shown as non-isocyanate polyurethanes, for example, biosource polyesters, or epoxy system without bisphenol A, for example, in that case, or phenolics without formaldehyde and phenols. We also work on rethinking about their formulation and shaping process, so saving energy and materials and solvent as you process polymers by photopolymerization, for example, which use a low energy amount, but also a short time of reaction, and allow also specific customization of the processing using 3D printing, for example. We work also on non-solvent based processing technique for thermoplastics as reactive extrusion, in which you can formulate, you can modify chemically polymers in a twin screw extruder with a very short time, few minutes, and it's a question of catalysis of reaction in high viscosity medium. And also, as shown before, also the use of microwave, for example, for synthesis and processing and recycling. So the important thing is also to design more durable polymers, and especially polymers which are able to repair and or self-repair, which is the crown of the system. And for that purpose, we are working on supramolecular chemistry of polymers, introducing reversible bond or reversible bonds which can be covalent bond or physical bond in order to prepare thermoplastics or crusting polymers. We already see that with the cans or the vitrimers, which allow to avoid this division in between thermoplastics and thermosets, recyclable and non-recyclable polymers. And the important thing also for durability is also to think about polymers or design polymers which are able to heal themselves during under a moderate external stimulus, or being able to self-heal by themselves. For example, that we are working on the introduction of breakable microcapsule, which contain healing agent, for example, which can heal cracks on coatings and things in order to have a longer lifetime for the polymers or for different things. And also that's very important to design polymer for specific use, because the polymers, the problem of recyclability, of recycling, is also that the polymers are used in so many applications that you cannot really know. And most of the time they have also combined several polymers to do several to be able to follow different function. So introducing multifunctionality for a single polymer is something very important. So we are working on allowing to reduce the use-step environmental footprint as, for example, lightweight materials and based on solvent-free processing methods as supercritical CO2 or bio-based ones, aerogels for thermal insulation, and the thermoplastic-based composites instead of thermoset-based composites. And also integration of many as many as possible functionalities in a single polymer. For example, I showed in the movie what we are doing with a polyethylene. That's a single polymer, which is a polyethylene, which is now super hydrophobic. This example is fully related for recycling purpose, because the idea is to be able to have inside the bottle, inside the package of based on polyethylene, polypropylene, to have a surface inside which is super hydrophobic or super oleophobic, in order that you remove all the waste as you can do, or the pollutant as you can do before recycling, before washing. So you use less water, for example, before recycling for washing. And finally, so that's examples from my lab, but I want to also to say something about that's probably more related to the first part of the workshop. But I'm also coordinator of a special part of what we call in France which is a French national initiative, which will go to up to 2028. And there is an acceleration strategy which is at the level of France, which is named Recycling, Recyclability, and Reuse of Materials, so including plastics, as you will see. And the idea for the French government is to speed up the transition to circular economy and to push the French society to this trajectory for decoupling economical growth and consumption of natural resources. And recycling is one of these. Is supposed to contribute to that on the budget. So it's concerned all the TRL. So I'm coordinator of the research, basic research part. So from TRL 0 to 2-3, which is given for the academic research, and the under a priority research program and equipment which is named Advanced Technologies and Socio-Economic Analysis for Ecological Transition in Recycling. And there are also actions. So this one is at the bottom is the action for academia and technical center, I can say. But there are also action for all the TRL levels, so valorization, demonstrators and things. So the whole strategy will concern something as 1.2 billion euro, and several tens of millions will be given for the program I'm in charge of. And the main objective for this research program for academia is to mobilize the research actors concerning fundamental, directed, or partnership research focus on recycling issues, technology transfer to companies, and the idea is to focus on scientific questions which are focused on understanding and mastering the phenomena underlying recycling methods and process, try to remove the scientific barrier related to recycling, which concern very, very different types of science, and stimulate the interdisciplinary project. So I just finished with that slide. So plastics are concerned with other materials as strategic metals, polymer and cardboards, multi-materials, textile. In another program, probably we'll have glass and other types of materials, but the objective is to focus on that 5 types of materials. So we launched different type of projects. So projects really related in materials, in each of the material. So for example, recycling of plastics, so recycling, mechanical recycling, chemical recycling, strategies for decontamination and things. So the heart of the material science, but also what we call transverse project. Because as you saw in the previous talks, I can say the scientists could do, from the academia, have all the tools to design more recyclable polymers and things. But the problem is really to have a kind of, they say, well, as some say about holistic or systemic approach, taking into account all the steps, and especially being able to know what is needed really. Is needed now and tomorrow, and what we need to design as polymers for tomorrow, what kind of process we need now to separate, for example, polymers and other materials to be to applied or science, the material sciences. So we have transverse projects which are related to some already known objects or field, as for example, how to treat the batteries, or a new technology or new technologies of energy, as the photovoltaics, the hydrogen fuel cells, the wind energy tools, and etc., and also the electronics and the electronics or the house waste without the bio waste. So that's very important to consider the objects, not just the materials, to know what exactly are the key issues and the technological and scientific issues. But also we wanted to have transverse project which merged which considers all the aspects as the economics and the politics, the regulation, and everything. So that's a project which will be launched, I think, at the beginning of the next year for 6 years. And that will be a way also to develop also collaboration with other countries in Europe, especially. Thank you very much for your attention.
Thank you very much. Thank you for sharing all the information. all the information about your research, as well as the calls from the French national agencies. I think you are really putting a lot of efforts on that. So I was very much taken up by some of your examples, like making artificial leather and super hydrophobic surfaces and all. I don't know, we don't have so much time left now. So I'm wondering if we just have 5 minutes. If you have any burning question right now, you should ask. Otherwise, we take it some other time, maybe at the end of the conference or tomorrow. There are no questions on the chat, Aileen? No? Shall we take a 5-minute break and then come to the next session? I think this session we have listened to a lot of good research going on, both on the polymer chemistry, the synthesis of building blocks, as well as the recycling. So thanks all the speakers. And 5 minutes, there is coffee outside, we bring it here, and then we start with Anders.
Oh, thank you. So we resume this session. So we're going to stay at state of the art of plastics design and recycling. And we're going to put the focus now on plastics recycled and the many aspects of that. So it might be interesting to know that about 100 persons are watching online. So it's just not this small community in the room. It's a big bunch of people listening in. And it's so great that you all could join us today. And don't forget that we will also continue tomorrow with a morning session, digging deeper into these issues. And then you're, of course, all welcome back. So now let's move on to our next speaker, Anders Daugard. We're so happy to have you here from the Danish University of Technology. You're here to tell us more about where do plastic fractions go. We're so excited to hear you answer that question. Please.
Thank you very much, Ulrika. So I don't know, maybe the title was a little bit bold, but I was sitting there and thinking, how should we start this? And when you talk circular economy, you talk plastics. I think one of the things that at least we at DTU spend a bit of time thinking about is also a little bit, what does it look like when it's not idealized on a piece of paper? So when we look at that, I try to draw this a bit simplistic view still, looking at the different types of fractions that we would see if we think about plastics and materials in general. That we very often think about a material that looks a little bit like the nice granulate we have out here. We think about products. We think about the first row type of materials, where we go through a processing. Everything is good and nice. We know the material. And then we go into some kind of product. And this is typically, often at least, where I feel that we stop the discussion. When we talk about plastics, we talk about how to recycle. This is what we're looking at. And I should, of course, say that Gerard actually just mentioned my point just a second ago, that we also need to talk about the less clean and the polluted cycles and how to get through that. So working here, that's pretty much simple. That's what we would normally call industrial recycling. It's taking place before materials even leave the factory. It's regranulated, it's just fed back into the process, and then everything is good and nice. This is possible for simple products, and it's something that most companies are doing today. Not everyone, but a lot of companies are doing this, and it's easy, and it's very easy to defend from an economic point of view. When we go on from here, and we go into the area where this has been in the hands of the consumers, things start to get a little bit more complicated. We muddy the picture a little bit, because we lose the link to the producer. And that's actually a very important aspect, that we, even though we do a lot of sorting, we can get a nice quality here in the terms of it being a relatively homogeneous distribution from a product and a materials point of view, but we have still lost the link to the producer, and it has been in use. And why is that important? Well, it's important because when a product has been in use, we also add a lot of non-intended additives to the materials. It's whatever the consumer has put on there. And that's actually essential in considering life cycle analysis and, well, not life cycle analysis, but the possibility to reuse the materials and bring them into a new life cycle, because they've been polluted. And that means they often contain heavy metals, even though there should have been no heavy metals close to the product. We can actually see when we analyze them that there are heavy metal traces in these. There are also other types of additives, just to mention some. but it makes it rather challenging to work on these, and basically, therefore, it often brings us back to household plastics being downcycled more than they're actually upcycled. So we have a lot of challenges in these systems. The industrial waste, as I said, is a fairly simple process in that it's possible to shred and reuse this pretty easily. We have all these good things about the materials, and it makes it really nice. But the point I really wanted to make is that this is something we can do when we have a monomaterial. And not all materials are monoplastic materials. So one of the cases that we've been looking at is approaching one of the classical cases in packaging materials, and that's both standard plastic packaging materials, but also multi-layer packaging. And I would like to start a little bit with why we're actually doing that. Because if we look at the classical plastic materials that you have here, and I apologize if you can't see this online, but you have the classical plastics up here on the top, where you have a pretty high penetration of oxygen into the materials. And if we're considering it for a packaging application, we really would like to be down here where some of the foodstuffs are. So these boxes down here, they resemble the need we have in order to protect foods. And I would any day argue that it's a much smarter thing to actually protect foods and conserve foods and therefore reduce our climate impact rather than using a simpler plastic and not being able to produce the foodstuffs. So balancing things a little bit here is rather important. So in some cases, we do need something like multi-layer packaging. Multi-layer packaging is, for those who are not so aware, it's typically something like this simple 5-layer thing, or it could be a 7-layer system where you typically have a barrier layer in the middle, and then you have a couple of compatibilizing layers, and then typically you finish it off with a polyethylene layer on the outside. So that's a relatively simple version of these. But the reason that we want to use these is because they move us from the area up here and then down into this area. Well, to be honest, they're actually moving us out here. So the multi-layer packaging is often actually even better than what we need in order to conserve foods. And that leads us a little bit into a research project we did a couple of years ago, where we looked at possibilities for replacements. So if I can go back, does that work? Yes. Just want to direct your attention to PLA, which is up here. So it's a little bit lower than some of the classic polyolefins, but it's not quite where we want to be. So PLA, we've already talked about. I don't want to go into details about that, but it's an interesting candidate for new types of polymers. But one of the challenges with PLA is that it has relatively poor barrier. It's a brittle material, and it also has longer processing time. So there's a lot of things there that makes it a little bit more costly to process using that. And it doesn't always cover what we would like to see in terms of barrier properties, for instance. So what we did was worked on putting nanocomposites into, or making PLA into nanocomposites to see what we could do with respect to barrier on these. Making PLA into a nanocomposite gives it better thermal resistance. So we can, by adding a little bit of nanoclay or nanocellulose, we can increase the thermomechanical properties of the PLA, which is interesting if we want to have high temperature stability, but it is also showing you a little bit that we can modulate the properties of the material by adding a low molecular weight, or not low molecular weight, a solid filler to the system. What makes it more interesting is that we can also reduce the barrier properties, so basically going from a relatively high oxygen transmission rate and similar for water, we can go down to about a reduction of 75 to 90% decrease in transmission rates of these relatively important gases when we think about packaging materials in general. So this shows that we can move this a little bit towards where we want to be. If we go back to the plot, that means that we are not up here, but we are approximately down here somewhere. So that means that we've moved into the area where you want to be with respect to water, but we're not quite there with respect to the oxygen transmission rate. Now you're probably wondering, why on earth did you then bring all of this up? Well, that is because this shows something else that we are working a lot on in different types of research projects that are also currently ongoing that I can't tell you about due to confidentiality reasons. But this approaches the advantage of having what you call a monoplastic system or single polymer system, where instead of having a multi-layer system where we will have the problem that if we do processing on a multi-layer system, we typically do film blowing. So when you do a startup on a film blowing setup with multi-system polymers like these, you have a huge waste resource. And that you can't reuse because it's a mixture of plastics. If we, on the other hand, can transition that into a monoplastic system, that means that suddenly we can regranulate this, we can reuse it and just reprocess it into the target polymer that we want. And like that, we can reduce waste in the processing part. So before it gets to the consumer, where it is still clean and nice, where we can easily reuse it for packaging and even food contact materials. So this is something that interests us quite a lot at DTU, and it brings us down to these three questions down here, where we would like to focus a little bit on what is actually required. Because I think sometimes you design multi-layer packagings because it's easy. We know that we're well within the window where we should be. But I think this whole discussion about circularity is a good cause for us to start wondering about what is actually required. Maybe we can live with a little bit less and find the optimum in there. If the optimum means that it's easier to process and it's easier to salvage some of the waste materials to better recycle and better use these systems in these cases. And that was exactly what Professor Gerard was mentioning just before, that this is an area where we need to work on more parts of the process. We need to work with environmental engineers where we look at life cycle analysis. We need to work with people who do processing. We need to work with the chemists who understand the material more fundamentally. And this is where we see that this is really driving forward, that we combine people with a lot of different backgrounds, and therefore we can shift things a little bit more ahead. I stopped a little bit early before when I was at this slide, because I stopped at this place. And if I should be honest, I should have put this place up where we have the mixed waste as well, out here on the right-hand side, which is probably a bit closer to the actual scenario, at least if we look at the waste fractions that we can collect in Denmark. But we also have this fraction down here, where we often see a mixture of foodstuffs and polymers in various contexts. And these are two other types of systems that are actually also adding another level of complexity to these systems. Our solution when we go into that is to look at two different treatment methods, where the first one is looking at mixtures of plastic and whatever being metals. It could be food residues, it could be wood fibers, basically applications where we for some reason have been unable to separate the plastic from a foreign element. Those cases are difficult to reuse for mechanical recycling, and we propose to do that by chemical recycling and pyrolysis instead, where we try to valorize components from pyrolysis processes, doing chemical recycling, and making new polymers from these waste materials. So that can be both from monomers, where we just had the discussion before with PMMA being an excellent example of something that we can actually recycle from, also material collected from consumers. Even though it is dirty, it actually gives a reasonably good polymer afterwards. You can do that with some systems, but there are also other systems where we get intermediate products that we are working on generating value from. So if you're interested, you can try to look at the QR code where you can approach our webpage for this Innovation Foundation Denmark project that's called Replastic, that works on generating new value from waste and, in this case, pyrolysis materials. On the other hand, looking at the bio-based materials, we've seen a lot of different cases of using bio-based raw materials to make new types of materials. We also think that's great fun, and we also think that it's a very interesting thing from a polymer chemistry point of view to go in this direction. But one of the things that I think one should think a little bit about here is also where do we want to put these types of materials in the context of recycling? Because if we talk classical plastics, we can do mechanical recycling. We can bring them back to the origin like that. There are cases where we can't. Then I think we should go chemical recycling through pyrolysis. What do we then do with the bio-based ones? Because those are not typically primed for mechanical recycling, because they are not sufficiently stable for that. And therefore, we need to think about other pathways. So this we're doing in collaboration with a large EU consortia that I believe Arne will also be mentioning in a second. But our pathway here is to look at how can we design these bio-based materials so that it makes it a little bit easier to develop a recycling pathway through the bio-based platform of polymers and plastic materials. So again, different parts of the process in this case. So just to recap a little bit, we're working on finding the right pathways for the different fractions, basically doing recycling and direct recycling by mechanical granulation and direct reuse of systems. We do that where our contribution mostly relies in doing synthesis of additives, for instance. We add something to the polymer in order to make it applicable to a broader use range. We can do chemical recycling, where we take care of some of these more complicated household waste fractions and see how we can use those again as a source of raw material to make new plastic materials, because we need to try to close the loop even from these more complicated fractions. And that's always interesting, challenging, yes, but there is value in some of these fractions. Even though we put them for pyrolysis, we do see cases where we can develop new value in these cases. Then we have the super interesting bio-based polymers that I think is super fascinating from a new types of polymers perspective, but definitely also requires us to think about the afterlife and how we're going to reuse these materials in order to benefit from having them in circularity. I don't think we can claim that one solution will fit all here. I would often claim that classical polymers are probably better for recycling because it's easier, they have better mechanical properties, but there are also cases where we can't prevent them from being polluted. And in those cases, I think we need to think about how we design our systems. And bio-based polymers are definitely part of that solution in specific applications for specific cases. But they can also be part of the problem. If they go into our mechanical recycling loop and we try to recycle our classical polymers with them, we're going to have big problems. So we need to further develop also our waste handling systems in order to make the next generation materials for waste handling. I would like to just extend a big thanks to primarily John Triffel, who did the work on the PLA. I haven't shown you much data on the other things that we're working on, but that's because I have some confidentiality clauses that I need to get around. Those resides in projects mainly for the Innovation Foundation Denmark and Horizon 2020 projects, where we try to approach the possibilities of recycled materials smarter and better, like everybody else is probably also thinking. So yes, thank you for your attention, and I'd be happy to take questions.
Thank you. Tack, Anders. Super interesting.
Thank you.
So this PLA material that you have, so that's intended then to reduce the overall usage of polymer by having this in-house recycling already in the process?
I think I lost you now.
Yeah, this PLA material that you showed.
Yeah.
You said that you can actually reduce this
yes,
plastic by in-house recycling.
So one of the problems when you look at multi-layer foils is that you extrude them with all these different layers, then you film blow them. But in the film blowing process, it takes a while to get that film actually blown. So that means that you have quite a lot of waste in that process. And already at that point, you have mixed the 5 or 6 different layers, and that means that you have a waste material. If we could do the same with a single layer material, then we wouldn't have that problem, because a single layer material we could always granulate, and then we could refeed it into the process, and then we could process it again. Maybe only as part of the process, maybe you'd have to add some things to stabilize the system again, depending on the fraction and the content of whatever additive is being added. But if we can simplify from having a lot of different polymers going in, and in the melted state where we have no chance of separating them afterwards, or there are chances, but then it gets complicated and it gets very biological, I guess. But then it would be nice to be able to granulate and rerun it.
Exactly. So it would be valorizing the scrap, basically.
Yes, and it would be valorized already industrially. And then still you have the potential that you can bring it to the consumers, you can recollect it, and then you can actually granulate it and reuse it as well at that stage. That's just a little bit further down the line. I think you already have a benefit from doing it already at the industrial stage.
Definitely.
And then we also get around all these food contact limitations.
So PLA does survive that scrap recycling? It is hydrolyzable after all, and a bit of a delicate polymer to treat.
Yes, and I would not say the PLA is the best example of that, but it shows very much my point. And then there are other polymers that it would be more relevant to do this too.
No, it's a really nice example of what you can do.
Yes, I think at least it was meant as an illustration of what you can do.
Great. So we don't have any questions in the chat, but we do have one in the audience, please.
I'm Leif Nilsson, I'm involved in the STEP program in Lund. Question about reusing scrap in-house in processing. When you do a laminate where you have, for instance, 2% EVOH in polyethylene, normally you say that is recyclable directly. And in recycling industry in Europe, we're talking about 2 to 5% is acceptable. What's your experience of where's the limit of the amount of EVOH in the film?
I mean, it's very difficult to say with different types of polymers where exactly the limits are. I think people are not 100% on where all those limits are today, but it's well known still that various types of polymers are not necessarily miscible together. So if you look at it as a miscibility thing, you could add an additive to make sure that you can process it, and then it makes it functional. However, that's costly. And then it ends up being a discussion of whether that would be a good idea to go in that pathway and compatibilize your way out of it, or if you should scrap it. And today, my impression from the companies that we talk to is that they would actually rather chance it, and then when the production fails, then they scrap it. And that's a little bit of waste of a material, but on the other hand, I also understand that it's very expensive to keep adding an additive that you don't need, and it's not necessarily a smart thing to do to keep adding an additive that you strictly don't need. So then it would be better to have it clean and be able to process without. So I think it's a very valid question, where should you be? But on the other hand, if you can do it without having the mixture of two polymers, you're definitely in a better place. And I don't think we get around making multi-layer foils. I just think we need to be selective of when we're doing them and when we need to use them. Then I still think they're a good solution because we need good packaging materials, and I'm still of the opinion that we do need plastics. I don't believe we can live without, and I don't think we can get our food consumption to work without plastic packaging. We simply need it to conserve the foodstuffs. But it's a super interesting question where the limits are. Also, when we talk about not only EVO and polyolefins, but also mixing different types of polyolefins and various types of nylons and polyolefins, and you can keep playing that game for a very long time. So but it's super interesting, definitely.
Tack. Great, thank you, Anders. And I think you pointed out something really important. You said you pointed out the importance of multidisciplinary collaboration to cover the entire value chain. And actually, our next speaker is going to address that very issue as well. I'm happy to present Rainer Hattikaul, professor at Lund University, and also program director for the MISTRA-funded program STEPS. So please tell us more about that. There you go.
Okay, yeah, here. Okay, thank you. Thank you, Ulrika, for the nice introduction and for being a co-organizer for this event. Okay, so I think whoever is listening here and who is sitting here seem to agree that plastic is going to be an important material for the future, for many applications. So in order to make a transition to a sustainable plastic system, you need a holistic approach over the life cycle of the plastic. So and since STEPS has been one of the co-organizers for this meeting, so I thought it would be nice to say something about what we are doing in the program. So let's see, how does this work? Yeah, Good. So how do we define a sustainable plastic system? Now, according to us, it would be low emissions, waste generation, and low waste generation. It is characterized by smart and efficient use and high material value recovery and circularity. Okay, and so now in order to make a transition to a more sustainable system, so our research is based on 3 pillars, so to say. One is to decouple the production from fossil feedstock. That means you go over to the renewable feedstock and maybe recycle plastic also. Then the plastic or polymer design that we have already heard about for improved reusability and recyclability is yet another pillar. And finally, which is a more overarching pillar, is the governance of transition. And that is something what we heard earlier, the first speaker of the day today. So by identifying the barriers for this transition and how do we govern the transition, how do we change the policies and all for making this transition more sustainable. So in this program, we are 2 universities, in Lund and 1 in Copenhagen, and there are 2 research institutes, RISE and IVL, and then we have 22 non-academic partners, which are potentially representing a value chain from renewable raw materials, plastic additives, chemical and plastic producers, plastic users, and also the waste management companies. And some of these companies have expressed a wish, or what they would like to see is, let's say, a bio-based textile fiber, which has good properties for that, wood coatings, dental products, food packaging, we heard about it just now, durable plastics and foams. And so it's quite a broad spectrum of applications which we are supposed to solve. Let's see how far we get there. Let's see. Now, when we come to the question of decoupling plastic production from fossil feedstock, it is we hear about bioeconomy, we hear about bio-based plastics, but one of the critical issues is feedstock sustainability. Do we have enough feedstock? And so far, whatever feedstock, renewable feedstock we have been thinking about has been going for production of bioenergy, but we need to consider biomaterials besides bioenergy. We need to prioritize future biomass use. That means because increasing demand for this renewable feedstock means that it is far exceeding the sustainable increase in supply of that. And now, with the rapidly electrifying energy system, it is possible that we may have more biomass available for biomaterials, which in turn will add more value to the biomass. And then, of course, there is this competition with the low-cost, high-performance fossil feedstocks. Fossil plastics, will we get over that? And that is also a struggle for producing the bio-based plastics. Okay, so now the raw materials that we are using in this program are based on our sugars and lignin from regional biomass streams, from agricultural residues and forestry residues. We also have some work going on carbon dioxide as feedstock and recycled plastic as feedstock. I will not go through all of them, but I thought it would be nice to know. Now, in making the renewable building blocks is what we are focusing on are developing technologies for production and also recovery of the products of the building blocks. So what we try to do is to take a biorefinery perspective in terms of resource efficiency. So that doesn't mean that if we are using glucose, we should throw away the rest. But we try to see, can we use all the fractions that are present in that feedstock? So we work on selection and design of pathways and catalysts or biocatalysts, and within the bioprocesses, we look at microbial processes, enzymatic cascades or chemical processes, electrochemical, integrated biological and chemical processes. We also look at biocatalyst development and all kinds of systems, procedures that are needed. process design, product recovery, and techno-economic evaluation and life cycle assessment. Just to do these, you can imagine that you need a lot of different competencies. It is not just technical. And some of the work that we have done and are still continuing is, for instance, the development of a furan-based platform. We have developed pathways for most of these molecules that are listed there. Then we also have these aliphatic diols and hydroxy acids and even dicarboxylic acids and even the aromatic structures that are of interest. Now, as you may have already learned from the different talks earlier, is in the polymer design, if you introduce the rigidity to a polymer, it increases the chances of recyclability. So one of the focus in the program has been to design these rigid structures which would lead to a high glass transition temperature of the polymers. So one of the inspirations was this polymer made by Chanstoft, which is called Akestra, where they have made this pyrocyclic monomer, which is introduced into a PET-like polymer, and it increased the TG to about 90 to 110 degrees centigrade. So within the program, the groups in the polymer technology, they have been making such let's say, diols, spirocyclic diols based on different bio-based molecules like hydroxymethylfurfural, levulinate, vanillin, together with the bio-based polyol from Chanstoft and making these monomers, which are called SLV for some reason. And then there has been some work done also on doing a preliminary life cycle assessment on using such diols in making the polymers. And as you can see that you have up to 46% reduction in the greenhouse gas emissions if you try to use these polymers instead of, let's say, a fossil 1,3-propane diol that has been taken as a benchmark. Now, one of these diols, which was based on HMF and pentyrethritol, was actually used for making for coating a floor in the student room in the chemical center where we work. And this is the guy, Niklas, who was making the polymer, and then the Buna people, which is a company in Malmö, they were doing the coating. And here is our expert, Nicola Rehnberg. He's adjunct professor at Lund University now, and he keeps testing it off and on. And for a couple of years, well, he tested it 2 years later, and the floor was still okay. Then it came Corona, and after that, I don't know how much he has done the testing, but still, this room is used quite a lot. So this is a polyurethane coating based on this diol that has been made in steps. And now, Niklas here, he worked further in making other diols, again using HMF and another polyol from Chanstoft, and he spun it into a fiber, a thermoplastic polyurethane fiber, and which with TG ranging up to 104 degrees. So they made about 150 meters of this fiber, and then he wanted to see if you can really recycle that, do a chemical recycling. So that means what he did was he subjected it to acid hydrolysis, and you get the products like DETMP and this methylene dianiline, and so he could recover at least not fully, but partly part of the polymer back into the for repolymerization. Yet another example which has been done at RISE is for making the non-woven fabrics. Apparently, in the non-woven fabrics, you have copolyesters based on terephthalate isomers, which are non-recyclable. So what they have done there, they have made a bicomponent stable fiber based on PBT, which has a butylene, a 4-carbon chain, and PHT, which with a hexane diol in between instead of the normal PET. And because of the difference in the melting point of these polymers, PHT having a lower melting point, so they subject that to chemical hydrolysis, and then they get a complete separation of these polyesters, and then they can recycle it. Anders talked about the food packaging. That is one of the most challenging packaging material that can be made into bio-based packaging. So there is one girl, one lady here, Karine Odelius. What she is looking at is she's analyzing the potential trade-offs between environmental benefits of bio-based plastics and their food protection performance. This is exactly what Anders was talking about earlier. What is more favorable to do? And then at the same time, what we are trying to do is to develop polymers which may have better, let's say, oxygen transmission rate or barrier properties than the normal bio-based plastics. So here they have been increasing the aromatic content of the polymer, and as you can see, the TG increases and the oxygen transmission rate decreases. But this is not, we have not come to the final work here, but this is the kind of work that is going on. Anders also talked about the EU project that we are in together, and that is about recycling of food and drink packaging in the food and drink packaging industry. Here we are looking at the depolymerization of the plastics, both conventional plastics as well as the bio-based plastics, and using the monomers as well as the bio-based feedstock to make the polymer again. So it's kind of doing an upcycling of the monomers. From our group, there have been, this is not related to STEPS, but there have been some startups that have come out, one based on PHA production. Here the main interest or the expertise was on the extraction of PHA, which is actually quite a challenge and contributes to about 50% of the production cost. And so the biological recovery system that is used that gives you native granules and also at the same time the single cell protein which can be used for feed, food or other applications. And the other startup deals with the non-isocyanate polyurethanes as well as BPA-free polycarbonates, again based on the cyclic carbonate technology. Now, finally, I would like to just show some slides on the work that is done on the plastic governance. And there is a group which is looking at a larger picture, not just making polymers or bio-based monomers. So what they have been looking at together with IVL, they have been studying the pathways for a sustainable plastic system. They started with 5 pathways, let's say bio-based, biodegradable, recycled plastic, and fewer types of plastics and reuse, etc. Now they have reduced the number of these. And so what they are doing really is to analyze the economic, environmental, political, and even cultural significance of these pathways. They have also been they're also looking at the challenges to these transition. So what they note is that there are few policy and governance initiatives that take a systemic approach to plastics. A lot of focus is on taking care of plastic pollution, but there is not so much efforts, or at least there's not so much talk about the upstream side of plastics. I mean, here, of course, the bio-based plastics also come into picture, but the upstream side would also influence the downstream part. And as we all know, managing plastic waste and recycling is messy and very heterogeneous within Europe. That we have heard of that before. Circular economy is a promising approach, but with large caveats. And chemical recycling, although very promising, it is not a panacea. We need to think of an overall picture. And they have been looking at the global wave of investment over the past 10 years in the petrochemical industry. And they say a fossil tide that must be turned. And so this continues today with huge investments in the plastic sector, because now the energy sector is going more non-fossil. And so in order to make the transition to a sustainable plastics, that will require investment in production, management, and recycling. And they have made this brief on plastics and sustainable investments for Mistra now. Finally, there is again a couple of persons, Johannes Triple and Carl Holmberg at Political Science. They have been conducting a survey among the Swedish public on, to look at the support, how do they look at the plastic-related policies. And this is a very recent survey that has been conducted. And what they find is that overall, among the Swedish public, there is a very high support for regulation of plastic and its use. But they also find there is a difference between demographic groups in the society. That means men and right-wing voters, they are more reluctant to support far-reaching policies. There is a broad support for expansion of the deposit refund scheme, which we mentioned, I think one of the talks that mentioned it, and that could be a step forward as it artificially maintains the value of the packaging after its reuse. So in the long run, there is a need to push practices towards high material efficiency, as in reuse, lending, sharing, and in some cases reduced consumption. And with that, I would like to thank you all for your attention, and also all the agencies that have been involved in funding, and also to Eva for enabling this session. Thanks a lot.
Thank you. Thank you. You're really sort of adding a perspective here, like lifting your eyes and looking at the entire value chain and a policy part of that, and how collaboration is needed for that. Mm. That's excellent. I think we need that alongside the chemical work to make this transition happening.
In fact, people hear these guys more than they hear our science. It is more easily understandable, I think, to the public.
Maybe so, but at least they're listening to something, and that's, I think, is a major achievement. Yeah. And I think also the next speaker will highlight this, and collaboration in transition. So it's a real pleasure to introduce the next guest from France, University of Lille, Dr. Arnaud Pony. Welcome to share your initiatives and how you work on collaboration for a transition to a more circular economy. Please.
So thank you very much for your kind invitation. So I will talk a little bit about what we are doing currently to bridge the world of, let's say, waste management on one hand, and the academic research on the other hand. So first of all, So first of all, we need to think that usually when we recycle plastics, in fact, we are not recycling plastics, we recycle products that contain plastics. And this is the first difficulty. And we have a lot of type of plastics. Well, you all know that. We have seen that many times today. But also we have a large manufacturer that use that plastics. And if we talk about different sectors that use plastics, then we will have different specificities of these plastics. Previously we talked about my colleagues that said we have plastics that need to be food contact, for example, for food packaging. But in agriculture, we're going to have different specificities when we use that. And we need that specificities, and we need to gather all that specificities, academics, I mean, in the group, and we will see that right now. So if we have the first challenge for plastics is mainly collection. It starts from that. And so what we have done is starting from the collection and the companies that manage the collection system, usually the product and offline. Then the second part, and collection is really important to avoid plastic leakage in the environment. Then we need to increase and to develop recycling, and in particular, as it was said previously, the quality of recycling, because we have problems on functional properties of recycled plastics. We have also regulatory compliance, for example, for legacy substances, for food contact, and so on. Then we need to align that with the incorporation part of plastics. Currently, in the plastic strategy, the European plastic strategy, it was said that only 6 to 7% of the plastics are coming from recycling. It's around 4 million tons in Europe. And finally, we have a problem of design and eco-design, as it was mentioned previously, with the different new material that you work on. And we need to align all that steps to be able to overcome that challenges. So this initiative was started by what we call EPR scheme in France. EPR is for Extended Producer Responsibility. So in France, and French government is highly relying on that policy to manage plastics. And it was started more than 30 years ago, well, no, less than 30 years ago, with packaging. I'm sorry, it's in French. I've added this slide this afternoon. And we gather all that EPR schemes to work on and try to gather them in a huge initiative to discuss and explain how plastics are really treated in France. Well, I mean, plastic waste are treated in France, and in fact, all these actors are collecting, managing, treating the waste. So they organize all the waste treatment for this waste. So it is packaging, I mean household packaging, it's products, agricultural plastics, it's also automotive, textile, that are in and furniture. And we have also printing cartridge that are also relevant because they have a lot of plastics, but they are currently not in our initiatives. And as I previously said, we have a lot, well, the French government is highly relying on EPR schemes. Just an example, we will soon have new EPR schemes that will come. In 2022, we're going to have building and construction. So this means that all the materials that are used for construction will have an EPR scheme. It's around 42 million tons product to be recycled, including minerals. We're going to have sports articles. We are going to have an EPR scheme for toys, and also all the materials that are used for gardening and for craft, I think it's the right word. So this is coming, and we are going to have, as you see, a lot of EPR schemes that will be that will manage the end of the product end of life. And what we did is that we started a plastic circular economy working group that is supported by all these PROs, so producer responsibility organization. So I mean packaging, agricultural plastic, weave, furniture, textile, and some of them will probably be the one that will look after these new products. And what we did is that we built that group to share knowledge, because in all that types of products we have different problematics and different problems, and the idea was to share knowledge, to share competencies, because we need to align all that technologies. We need also to explain how recycling operations are really done in real, and in the different EPR schemes, because we never recycle a like we recycle a packaging, for example. It was also introducing the challenges and the research need that EPR schemes have identified in their streams. And finally, to network and design new collaboration, because we have a lot of researchers in France, but they don't know each other. There are several, usually they know, well, 1, 2, 3 groups, but we need to have an holistic view also in the academic system. So the idea is to organize 3 meetings per year. We spend 1 day all together. We usually work with a session, 2 sessions each day, with a morning session that we explain specific topics from the EPR schemes and also the news, like what Jean-François Gerard presented previously, the new call for project. And we also always do an introduction of the newcomers, so the new groups that are joining may present what they do, how their group is working. Do they have specific equipment that would be interesting for other groups, and so on. And usually the afternoon session is related to selected topic, mainly scientific, academic topics, but with a vulgarization degree that is important, because we have a lot of different groups inside. So currently we have more than 70 academic registered in that initiatives, and coming from more than 50 teams, different teams, all over in France. And with a large panel of competencies, because it's, whoa. It goes from polymer synthesis to sorting and handling, for example, optical sorting, electrostatic sorting. We also have recycling technologies, mechanical, 3D printing, chemical recycling. We have also teams that are really good in mechanical and also aging, so characterization of this polymer. Analytical science, as I said, it's a key issue and a key topic for the next year. The analytical science, one of the previous presentation was talking about the case, for example, of non-intentionally added substances. So this is a key issue, and we need also to have sectorial application. So we have teams that are really experts in textile, in packaging, in buildings and construction, and we need to have all these to have a good way to, well, good chance to develop projects that are interesting. So for each meeting, we are we gather around 30 participants in a room, but we have also hybrid system with now with the COVID the opportunity to gather people with Zoom. It's free for all academics, So it's supported by the EPR schemes. This is in their objective to support R&D. And workshops topics include, well, we talked about sorting technologies. So all the researchers that were there were experts on sorting, explained what they do. We talked about biodegradable plastics and how we measure the biodegradability, for example, of PHA, how we can convert these bioplastics, the impact also of material engineering when we recycle them. It's a key issue. How it impacts recycling and also the durability of the new plastics we have regenerated. The case of decontamination for food contact, but also for legacy substances, for COV, VOC, sorry. And also some question about the chemical compliance of post-consumer recyclates. And with that, we initiated new collaboration. So here is some example that we have obtained. So one is about the extraction of brominated flame retardant using supercritical dioxides. So it was two groups that were not collaborating. They didn't know each other when they started just that collaboration. The other one is the sorting of that brominated flame retardants. And here it's a collaboration between academics and an EPR scheme that is managing that plastics. So the idea was really to facilitate the networking, and that's a key issue, and that's why I'm here today, is that networking and collaboration is a key issue for plastic circular economy. So thank you for your attention, and thank you for your invitation.
And thank you for highlighting such a beautiful initiative to really make people collaborate. I mean, this is really what we want to do. And as you say, multiple competences are needed.
Yeah, man, and you feel free, if you want to build new collaboration, feel free to send me an email. You have my address here. I will help you to find the right competencies, because we have a huge network now. And with all the different, so if you want to build a new project, European project, well, I'm doing that for all the academics we have in the network. So feel free for that.
Thank you. And you're actually not talking only to this room, but actually to the still 100 viewers that we have online. So you have a big audience here that's listening in. Thank you. So you mentioned among the multiple competences, you're actually mentioning eco-design.
Yeah.
And our next speaker is a true expert in that, so it fits just perfectly. It's a great pleasure to introduce Professor Mattias Lindahl from Linköping University. You're also program director of another MISTRA-funded program, RES, on resource efficiency.
Yes.
And that's a really important competence that comes into play here.
Yes, that is correct. And yeah, I'm really happy to be here today, and I will give a presentation that hopefully will open up your mind a little bit. I will give you provocative thoughts and ideas, and it's about effective and resource-efficient solutions, obviously logical. And yeah, in the old days, when we design products, and actually the way we lived, we were actually living in a society with few resources. So when we design and produce products, we design them to be durable, easy to repair, etc. Share. And we actually tried the best to not produce waste, because waste was something that was not appreciated by anyone. And we really utilized things. And then we got the Industrial Revolution, but we kept on doing this thing, producing things that are durable, etc. But what happened is that, of course, if we continue to do this, and we are mass producing and utilizing the business model of selling things, we get secure market. And that was actually what happened. And people started to be very, very worried because we had a transition from the countryside to the cities. A lot of people living in fast-growing cities, and it was, people were afraid of social disorder, and that was something that no one really appreciated. So, but that was, hope this works now. That is how we actually then started to have our society. And I like Peter Drucker. He has stated a lot of things over the years. And one of the things he wrote and stated was, the greatest danger in times of turbulence, it's not the turbulence, it's to act with yesterday's logic. And I think this is really a problem. Coming back to what I just mentioned, we built a society, a linear society, where we listen to this type of guys. This is Victor Lebov. He was very, very influential when it comes to influencing the automotive industry. He summarized his ideas in this paper or article that came out 1955, and he stated, our enormously productive economy demands that we make consumption our way of life, that we convert the buying and use of goods into rituals, that we seek our spiritual satisfaction, our ego satisfaction in consumption. We need things consumed, burned up, replaced, and discarded at an ever-accelerating rate. And in this context, plastic is a perfect material, right? Cheap and produce a lot. You can make it also designed, because I'm an engineer, designer. It's easy to design a lot of things that are perfect in line with this, especially if you are boasting one way, the linear model. And then we started, we became consumers. And we started to talk about waste. I've heard the term waste several times today. But I would say it's not waste. It's a raw material that you're using into your processes, because then you should call it what it is. It's a resource. It's not waste. Because if you start to talk about and consider it to be waste or second-hand material, you immediately take down the value of the material. And also people get a little bit suspicious about the value. I will give you an example how stupid it is to talk about second-hand products and waste. Let's say I'm selling towels, and you think, and you're in need of a towel, and they are fluffy, nice towels, and yes, the price is correct. Then most likely you can think of buying a towel from me. But if I tell you it's a second-hand, it's the same towel, suddenly you start to be skeptical. Is it clean? Even if you can think of buying it, but not for the same price, it must be a reduced price. And at the same time, I'm quite sure that all of you have been staying in a hotel, and I've so far never seen anyone coming down to reception complaining about the fact that they are using second-hand towels in the room. And that those towels have been used in a lot of places that you don't want to think about, and they have been used by a lot of people over the years. And even the blankets are second-hand. But there we buy it. And by the way, most of you are living then, if you continue in this way, in second-hand flats and houses. But you're not calling it second-hand then. Anyway, but Victor Lebov actually managed to provide us with the logic that we now realize is not the most suitable. So what we're doing in this program founded by Mr. Rees is that we want the industry to actually transform and transition towards more circular business models where we are focusing on doing not only things more efficient, but actually the focus on what is effective. Because I think that is also a problem Because in general, in our lives, we have been taught we should always try to make things more efficient. And we continue to do that. But the problem, coming back to what Peter Drucker stated, it's okay if that logic we're following is smart, but we should never have the starting point that we try to make things more efficient. The starting point should always be what is the most effective thing to do, what is the right thing to do, and then try to make that efficient. And then we need sometimes to rethink the way of doing things. And here today I've been listening a lot about developing a lot of different types of new plastics and so on. Not sometimes or questioning why do we do it, some did. I think the starting point should be, and it was highlighted by some, that we should think what are the reasons why we do have this plastic? What are the requirements? Sometimes we have thought now, I mean, we are talking about food, need to preserve foods and so on, but is it really needed to have food and meat that can sustain in the fridge for 10, 15 days? Or is it something that we have just developed because of Victor Lebon's ideas? Maybe it's enough with less requirements. We maybe should change things, how we do things. And what we focus on in Mr. Rees is this. This is a figure me and two of my colleagues, Tomiko Sakao and Erik Sundin, developed some years ago. It's also available in the first standard for circular economy by the British Standard Institute. And he's tried to illustrate this, what we should focus on. Because the main environmental impact normally occurs during the use phase. And that is a problem. But when can we then affect this? It's during the the design phases. It's during the design phase when we design the packaging, design the solution. It's then we can actually reduce the total environmental impact. If you are done wrong there, and we're not talking about the product, I'm talking also about the solution, not only the physical product, but the whole system. So it's very, very important that you get in the right requirements there. But then we maybe need to rethink what type of requirements we are dealing with here. Sometimes questioning the current requirements, is it really necessarily so that we should design and put requirements that food packaging for meat should be able to store the meat for 15, 20 days or something like that? Or maybe it could be shorter. Then the problem here is also that we are not been questioning how many different types of products we are putting out or types of versions. And when it comes to plastic, I'll come back to that on my last slide. This is a challenge. So what we also do here is that we try to see how things are connected. And I liked the French presentation just before here, because I think it's important that you connect people with different perspectives and backgrounds. Because it's not only to come up with better plastics or formulas, etc. You also need to have a deep understanding about the applications where they are used, but also the business models and the legal framework around it. And it's a risk that if we are not considering the whole picture, we are continuing to use the old logic. It might be so that we should change, for example, the policies and regulation in order to have a better fit for the future. Or change the business model, because one problem when it comes to plastic materials is that the producer are losing track of the material during the business model. So actually I'm really, really happy. Ryan and I, we have this project, Unity, and it's a circular plastic society based on a few thermoplastic with high performance and clear specific properties. And here you have a lot of questions, but the idea is, could it be that we actually could reduce the number of different types of plastics? Because if we could do so, that would be interesting. But what will then be the implications, not only for the material recycling or reuse, but also from the production perspective? And I know this is a provocative proposal, especially if you're developing a lot of new formulas, etc. But I would say in many cases, I think it would be possible to actually cut down the different types. Because if we cut down the number of different types, it will be easier to take back. We'll have higher volumes, etc. I'm not stating that we should stop innovation or innovating and find out new types of formulas, but we should be a little bit more restricted when it comes to actually introducing a lot of new versions of plastics types, etc. Because they're causing problems. So with that, I would like to thank you all, and yeah, please if you have questions. I'll go back to the questions to you.
Tack, Mattias.
Yes.
And thank you for also daring to raise these inconvenient facts,
yes,
and asking the inconvenient questions, because that's really, we have to put everything on the table to get the discussion going. So I think that's really important.
May I steal just a few more seconds? Actually, the basic idea behind this came from, I visited Japan many years ago and had a lot of discussions with the electronic industry. And then they had done a survey. How many different type of plastic they actually use in the products? And the big companies asked the engineers, and they had around 10,000 different types. Then they also asked, how many do we need to actually perform all the needed functionality? If you really need to cut it down. And I don't remember if it was 10 or 11. But the thing was that none had ever questioned. And everyone was eager, try this new one. But the main benefit from cutting down would be not in the end-of-life treatment, but actually in the production, because it would be much more convenient to handle less.
Very interesting perspective. Thank you, Mattias. Great, and thank you everyone online, everyone in the room. Thank you for participating today. Please know that we are resuming tomorrow with a morning session. And that also goes, so if you later on, maybe tonight, think of this great question that you really wanted to ask, it's not too late. So we will, of course, also open up the chat function tomorrow when we're online. We will be on Zoom tomorrow, right? So you can then type in your question and we'll sure to moderate it and direct that to the relevant speaker. So it's not too late. Thank you, everybody, for watching. We'll be back tomorrow and we resume at 9. For those of us who are here, please, you're invited to a mingle session upstairs. And then you can, of course, also ask questions to the speakers that are here today. Thank you, everybody, for today, and we'll meet back tomorrow.
Thank you.